motivated by some strong requirements. So as you heard from Greg on Tuesday, the main objective of the CLIMA project is to quantify and reduce the uncertainty on physical components of climate models. And typically in ocean models, the largest source of uncertainties are the parameters and the parameterizations. So the objective of the CLIMA project is to tackle the parameterization problem by leveraging as much data as possible from observation and high fidelity data, and perform automatic calibration of these parameters in a global context. And hopefully the objective is to get to a calibration of the whole Earth system model. So this objective is quite ambitious, but arguably could have been achieved with existing ocean models. But we believe that there is a lot of advantages in rewriting a new model, and this is the main advantage is that we can leverage modern programming languages and new architectures. So there's been a lot of talk of GPUs in this conference, and this is one of the main objectives of rewriting a model from scratch. Now, leveraging modern programming languages for us is very important because it allows us to write the model in a high-level language that is much more accessible to non-computational experts, and in that way is easy to make a model more flexible and to create a user interface that can really open the model to users. And we believe that this is really what can accelerate the scientific development in the model, because the model can become a playground for testing new ideas and new parameterizations. Also for people that don't really know how to code in Fortran or how to really access complicated infrastructures. Going to computational efficiency, well, the reason why we want to target new architectures is quite simply because we want to use GPUs and we want to have a faster ocean model. And computational efficiency is quite key to the CLIMA project because of two main reasons. First of all, we want to move away from the mesoscale parameterizing paradigm. And we think that there is enough computational power nowadays that we can explore more systematically ID-rich ocean models. But to do that, we necessarily need to use GPUs. Like, there's no other way around it. And this becomes even more important if we want to perform this exercise of doing a global calibration, because global calibration is inherently a very computationally heavy task, because we have to run an ensemble of models in parallel. And it becomes even more important if we want to do this exercise at high resolution. So that's why we believe that rewriting a new ocean models from scratch has its benefits. Now, before going to the high resolution aspect, I want to spend a couple of words talking about the main achievements of oceananics, or what we believe are the main important features and advancements that oceananics gives to the field. And in particular, oceananics is written in Julia. So Julia is a fairly new programming language developed at MIT, which is just-in-time compiled, like the programming languages we saw in the talk yesterday. And so it means that Julia is easy to interpret, like a language like Python and MATLAB, but it has the computational speed of compiled languages like C and Fortran. And most of all, Julia is very portable. So oceananics runs on CPUs and GPUs, on laptops, on large machines, on Windows, Linux, and whatnot, with virtually no startup time. So it's very common for students to download oceananics and start using it and getting results in about 30 minutes. So this really increases the accessibility to an ocean model also for students and for people that do not really know how to compile a code or how to work on large clusters. But the main achievement of oceananics, and arguably the reason for its success, is probably the user interface. Because oceananics kind of breaks the tradition of ocean models that use a name list input for the model, because it has a programmatic interface. And this means that it works a little bit more similarly to a Python library, where you can import the model and include in your user script, inject user code into the source code, and even extend the model to your liking and test new ideas and implement new parameterization very easily. So there's an example here of a typical workflow in oceananics that really highlights how usable and interpretable the user interface is. And we believe that this is really the reason for the success of the model for the moment, because we have a lot of users, and oceananics is really widely used, especially in the large eddy simulation context. And we also have a lot of contributors to the code base and a wide community of users. Okay, so we are in the high resolution of ocean modeling session, so I want to focus in this talk on the reasons why we can achieve high resolution. And this, unfortunately, has to do only with our GPU implementation. So this is going to be a little bit more computer sciencey talk, unfortunately. And what we do in Oceananigans and ClimaOcean is not necessarily extremely new in terms of GPU computing, but because we just really follow the playbook and the rules and the recipes that allow us to get efficiency on the GPU. But we believe that ClimaOcean is the first instance of specifically an ocean model that demonstrates what you can achieve when just rewriting a code for GPUs. So we think that's why we can achieve this performance. And we can do it because we really started rewriting the model from scratch. And the main three objectives that we try to follow when writing the code are, first of all, fast compute. And this is because GPUs are not powerful because they have powerful cores, but because they have many of them. So when writing an ocean model for GPUs, it's important to make sure that you expose the parallelism in the algorithm, so to map the algorithm very well on a lot of threads. The second principle is memory leanness, and this is because GPUs are extremely RAM limited. So it's very important to try to keep the model as slim as possible if you want to make efficient use of the compute resources. And the third principle is scalability. And this is because GPUs are ironically very fast, but communication is not faster on GPUs than on CPUs. So you really have to think a little bit more about how you implement communication when running on multiple GPUs. So starting from our actual algorithm, so for who doesn't know, a GPU function is called a kernel, and is launched on a block of on a grid of threads. So these threads, think about cores in a CPU. So they're the minimal working unit on a GPU, and they work in parallel. They work together in a single instruction, multiple thread fashion. So when writing a function for a GPU, you're basically mapping a function to a block of threads. So it's important to figure out what configuration is the most efficient in your algorithm. So in terms of the equations that we're solving, we started with arguably a simple algorithm. We followed the MIT GCM lead. So this is just a staggered C grid and a Z vertical coordinate and solving the primitive equations. And this is probably not the most fancy in terms of vertical coordinate, but it's a very efficient, very simple algorithm that is very easily parallelizable on GPUs. So it's a very good starting point to write an ocean model on GPUs. And we divide our algorithm in 4 macro areas that are shown here in different colors. So in green, we have arguably the most computationally expensive part of the code, that is the computation of the 3-dimensional tendencies. And this includes the advection, the Coriolis term, the pressure gradients, and the lateral physics. And these are heavy computations, but they are parallel in nature. So it makes sense to map exactly one computational cell to one thread in the GPU grid. So in this case, one thread holds the computation of the whole cell. We cannot do this for the parts of the algorithm that include vertical logic. So in this case, it's the implicit vertical diffusion and the integrals to calculate the vertical velocity and the pressure, the hydrostatic pressure, because these include a sweep in the vertical direction, either because of the integral or because of the solving of the tridiagonal matrix. So in this case, since these are serial computations that are no-go on GPU, it makes more sense to have each thread hold a computational column. So in this case, we spin up 2-dimensional kernels. And finally, we have our barotropic solver. And here's where we deviate a little bit from the MIT GCM, because the MIT GCM uses an implicit free surface solver that is essentially just the solution of a very large, sparse linear system, which is actually not very well preconditioned. And this is known to be extremely bad on GPUs because preconditioning on GPUs is very difficult. So in this case, we found out that switching to a split explicit formulation is actually very beneficial for us. So in our model, we're using a split formulation of the free surface. Going on to memory leanness. So this is a concept that is quite key to GPU computing. So each GPU code really tries to keep the memory footprint as low as possible. And this is what we do also in our software. So on the bottom right, there's a quasi-global simulation at 1/4 degree with 50 vertical levels. And the memory footprint of this simulation is about 15 gigabytes. So it fits very comfortably on just one GPU. And to show how we do this, I'm showing the example here of just computing the advection term in the right-hand side of the transport equation. And in the yellow box, you see how you would do this probably for a CPU code in finite volumes. So in order to not having to compute the fluxes twice, typically what you do is you compute the fluxes, you save them down in a temporary array, and then you compute the divergence on a subsequent step. And this is actually very good practice because it allows you to not compute the fluxes twice. So you're just reducing the computation. But in our case, we find out that the trade-off of this lower computation versus the memory that we have to allocate to store those temporary arrays is not worth it. So what we do might sound a little bit stupid, but it works. So we are actually computing fluxes twice. What we do is we pack as much as we can in one kernel, and we compute the whole right-hand side in one go. And in this way, we really can manage to fuse all the kernels together. I do aggressive inlining on the tendency. So our code basically requires to allocate just the prognostic state and a couple of additional auxiliary variables, and that's it. This is how we keep the memory footprint at a minimum. Now, I want to talk a little bit about our numerics also, because I think that's where we deviate a little bit also from the MIT GCM in our dynamical core. And this is also motivated by efficient execution on GPUs. Because on GPUs, there are schemes that work and schemes that do not. And schemes that work are extremely compute bound. So you want to keep your computation as maximum as possible when you retrieve a byte. So in this case, in ClimaOcean, we thought that we could give a shot to a class of nonlinear schemes that are extremely computationally expensive. So they require a lot of computation when you retrieve a byte, because we don't really pay the full price for them. And I'm showing this on these plots on the left. So this is the number of operations, the ratio of the number of operations required for these type of nonlinear schemes in ClimaOcean versus the number of operations required for a linear reconstruction of the same order. And you can see that the number of operations is upwards of a factor 20. So you need like 20 more flops per retrieved byte to compute a nonlinear advection scheme. But the price that we pay is showed here in the bottom plots on the CPU and the GPU in terms of ratio of wall time required to compute the advection term. And this is on the same exact code on CPU and GPU. And you can see that on GPUs, the price that we pay is at least like maximum 2.5 times using a very nonlinear advection scheme. Well, on CPUs, you go up to a factor 5. So we thought that since we have GPUs, we can really try new ideas and implement high-order advection schemes. And in this case, the schemes I'm talking about are WeKnow. So there are probably a lot of people know what WeKnow are over here, but I'm just going to do a review. They are, wait, these are not working. Oops, they don't work altogether, but whatever. They are a class of very nonlinear reconstruction schemes where the nonlinear weights are computed as a function of the smoothness of the advected field. The schemes were developed in the context of high Mach number compressible turbulent flows, where modelers had to get around the problem of having shocks in their solution. So shocks are gradients that are definitely below the grid scale, and you want to be able to preserve as much as possible of these gradients without really developing spurious noise that is typical of having high gradients in a finite volume code. So in theoretically, these schemes are minimally dissipative, but they also have minimal noise, which is basically the best of both worlds because you're going high order, but you're not getting the noise that is associated with going high order. And so we thought that these schemes are actually very, very helpful, especially in the context of eddy-rich ocean models, because in eddy-rich ocean models, we really care about trying to resolve as much as possible of the mesoscale spectra. So having a scheme that can give you an effective resolution will buy you some compute efficiency, basically. And as an added bonus, the schemes are implicitly diffusive, so they do not require any type of stabilization or explicit dissipation. Because typically when you change resolution, when you use dispersive numerics, then you really have to tune the viscosity parameter to try to keep your solution stable and try to have the minimal dissipation that you can achieve. And this viscosity is really not a physical quantity. It's just there to make the model stable. So by using the schemes, you don't have to do that because the scheme adapts to resolution and keeps the model stable, whatever resolution you have. Well, there's a caveat that they work a little bit like LES schemes, so you cannot really, the grid size has to be in the inertial range, because if you don't have a little bit of turbulence, then they're not worth at all. Like in very coarse models, you cannot use them. There are some downsides to using the schemes. And the first one is the low control on the dissipation. So we don't really have an explicit diffusion operator, so calculating the dissipation becomes very difficult, especially because the schemes are very nonlinear, so separating out a dissipative part becomes quite difficult. So basically, one of the the good parts of these schemes is that they don't require an explicit diffusion. It's also one of the downsides because you cannot really measure what this diffusion is. And the second downside is dipycnal diffusivity, because the schemes are not really commonly used in ocean modeling. So they're used more in engineering flows where they don't have this problem of trying to keep trying to lower the dipycnal diffusivity. So we really have to see if we're doing something stupid or not when implementing these type of schemes. And I'm going to circle back to this later. So verifying that using Wino we can achieve a high resolution is quite simple. We've done it in many configurations, and we always find out that we get an increased resolution power. And I want to show you two examples, one in a non-hydrostatic regime and one in a hydrostatic. So, oops, okay. Yeah. So this is an example of upper ocean mixing, where led by Xinkai in our group, where he compared using Wino schemes without any explicit diffusion to center numerics using a subrescale closure that is physically motivated. And he checked the convergence with an isotropic spacing of 2 meters versus 0.5 meters. So this is a case where the boundary layer will develop because of wind stress and cooling, and temperature and salinity will mix. And this is the end of these plots are showing the end of the simulation in terms of horizontally average temperature profile and horizontally average salinity profile. And what we found out here that was actually pretty surprising for us is that using a Wino scheme outperformed quite a lot using a subrescale closure that is physically motivated. And this is because the Wino scheme converges at 2 meter resolution, while the subrescale closure case converges at 0.5 meter resolution. So just by using better numerics or higher order numerics, we are increasing our effective resolution of factor 4. And that means 4 in every direction plus 4 in time. So it's a compute saving of a factor 256, which is kind of difficult to ignore. So this was quite promising, and that's why we thought, well, we can probably, since Wino works better than a subrescale closure where the subrescale closure is motivated, well, maybe it will work better also in an ocean model where the viscosity is not really physically motivated. So we applied the same concept to our primitive equation, and we found the same results. So on the right, I'm showing the Gulf Stream calculated at 12th degree. We're using a centered scheme with an explicit diffusion. This was a QG scheme. And at the bottom, I have the solution with using only Wino for tracer and momentum. And it is quite clear that even at this resolution, which is considered to be mesoscale resolving, you still have more structure appearing when using a higher order scheme. And it's not only that the solution is less diffused with a higher order Wino, is that the currents are sharper. There are more subrescale, there are more small scale vortices, and the gradients are preserved more efficiently. And we verified this also by looking at the kinetic energy spectra. So that is shown here on the left. This is not the kinetic energy spectra of the Gulf Stream, but it's just in the Southern Ocean, but it's the same simulation. And we tested also a 1/6 of a degree using higher order Wino versus the centered advection scheme. And we found out that at a 1/6 of a degree, Wino matches pretty well with the QG solution. So this means that we are buying a factor of 2 resolution also just by using the scheme. Also in a mesoscale resolving or eddy-rich context. Okay, so this was just for the numerics, and I want to a little bit close the loop when it comes to the performance. I want to revert back to performance a little bit and talk about the scaling of the model, because scaling it's a little bit more difficult to obtain on GPUs than on CPUs because of the fact that communication does not really get faster once you go on GPUs. So basically, virtually all the CFD GPU codes use some type of communication computation overlap, meaning that you spin up you launch the asynchronous memory passing, and in the meantime, you're doing some computation behind the hood. And this is quite easy to do for the baroclinic variables because we have very large kernels, and it's very easy to divide a part that depends on the interprocessor boundaries, an interior part, and a peripheral part that does not. So you just start the memory passing, compute the kernel of the interior part while you're communicating, and once the communication is finished, you just compute the peripheral part. And this is the easy part, and a lot of GPU codes do this. But the real problem for ocean models, the real horrible part for scalability are the barotropic solvers. Because if you do implicit free surface solver, well, that's a sparse linear matrix solution, and that's pretty bad. And if you use a split explicit, well, now you have to communicate a lot of halos each substep, which will dominate your cost. So what we do in our shenanigans might sound a little bit stupid also, but it does work. So we take advantage of the fact that we are very memory lean, so we pack a lot of cells in one GPU, and we extend the halos of the barotropic variables. And we make those halo active. So we are computing the free surface also on the halos. And since the number of halos are equal to the number of substeps, we can just do the communication once per barotropic substep and not per substep. We have more computation, but we don't care at all about that extra computation. For us, if we do 50 substeps or 100 substeps, it makes no difference. We don't really see that computation. But the interesting part is that we do only once the communication, and since the barotropic solve and the implicit vertical diffusion are commutative, we can hide the communication of the barotropic variables behind the implicit vertical diffusion. And this means that we're hiding all the communication behind computation in our code. And this makes a ton of difference, actually, because we think that this is really the reason why our model is probably more computation efficient than other GPU ocean models. And I'm showing here the share of computation of the different parts of the algorithm in a 1/4 degree ocean model on 4 GPUs and 1/48 degree on 256 GPUs. And the interesting part here is that the 3D tendencies are effectively the largest part of the computation. The barotropic step is almost negligible. It's less than 10% of the computation, which is a big achievement for us. And communication is non-existent, so it's completely hidden behind computation. So these are our final numbers for the scaling. We tested the dynamical core on up to 1,024 GPUs on 800 on the Parameter cluster. So on a 1/4 degree simulation, we get about a little bit more than 25 simulated years per day on 4 GPUs. At a 1/12 degree, we get about 10 simulated years per day on 64 GPUs. And this is basically it's 16 to 8 nodes, depending on how many GPUs a node has. And for us, this result is quite important because 10 simulated year per day, we consider it as a threshold for a simulation to be useful for climate projection. If you get lower than that, then it starts to be difficult to use that for practical purposes. And we get this threshold on a very limited amount of resources at a 1/12 degree, which is considered to be an eddy-rich model. So we believe that using CleanMotion, we can really try to explore more eddy-rich configurations without using mesoscale parameterizations. Now, there's a caveat here, is that these results are for the dynamical core only. So they are a very simplified simulation with prescribed fluxes, and they don't account for a lot of possible bottlenecks that we'll have in the future because we're implementing CleanMotion now, so a lot of new components will probably have a cost that we're going to have to account or optimize. And in particular, some examples are the input-output that might be heavy for us, surface flux computations, or the CIs that we haven't coupled yet. So that might be a big cost of the simulation. But realistically, we think that we can keep the cost within a factor of 2 of these numbers. That is roughly our objective. So we think that really, wait, let me see if I can show you the video here that it shows better. Here we go. So we think that really using GPUs, we can reach a new dynamical regime for the ocean. And this is the example of the simulation that we did just to test the performance at a 1/48 degree. The simulation was quite wrong. I mean, a lot of parts were missing, but it was just a proof of concept. But we run for a simulated year on only 32 GPUs. That means 8 to 4 computational nodes. And the whole simulated year took only 15 days to complete. And here you can see like some mesoscale that are moving from north to south on a seasonal cycle. And yeah, so this simulation really, we think that it proves the fact that we can achieve these types of resolutions by using GPUs. This might be not very useful for practical purposes, but it's very useful for scientific development. And We did this test also on a, oops, let me go back to. Yes, we did this test also for a longer time on a lower resolution. So this was a 12-degree simulation with 100 vertical levels, semi-idolized. We ran it for 20 years with a prescribed, with surface forcing that was done with prescribed fluxes and restoring to temperature, to climatological temperature and salinity. Also the simulation, I mean, the output of the simulation is not terribly useful. But it was just a test of the numerics of the model and the stability and the performance. But I thought I could share some results just in terms of kinetic energy. So the model was initialized from acquiescent state with temperature and salinity interpolated from the echo reanalysis. And the kinetic energy just jumps up in the first 2 years and is stabilized around 37 centimeters square per second square, which is a little bit lower than the 50 centimeters square per second square that is observed, but it's kind of on the high end of eddy-rich ocean models. And the model spins up its own mesoscale turbulent field, which compares quite well with observation and theory. And this is shown on the plots on the right, where I'm showing a snapshot from our simulation and from the Aviso satellite data. And spectra on the right-hand side in particular regions that show that we actually capture large-scale energy quite well. And also the spectra decays with a minus 3 roll-off that is consistent with theory. There is a bias in the large-scale pattern of eddy kinetic energy. So in particular, the Gulf Stream does not veer north above the Flemish Cap like we see in observations, and Falkland current is a little bit too strong. The Eastern Australian current is a little bit too strong, and Agulhas rings persist a little bit too much and are not dissipated as we see in observations. But we don't know how much of these biases due to the model itself, or it's due to the fact that we have an idolized forcing. So when we'll run a more realistic simulation, we'll probably figure out what the actual bias of the model is. Okay, so I want to circle back a little bit to diapiconal mixing, because we have now this new model, which is undoubtedly fast, has new numerics, and we have to make sure that we're not doing anything extremely stupid, and our model does not destratify completely immediately. So this is a project that we're doing with Jean-Michel that developed a new metric that allows us to compute point-wise, locally in space and time, the diffusivity that is due to the implicit advection scheme. And this metric for us is not only important because we are able to look at hotspots of diapiconal diffusivity, but also because it kind of closes is the last piece of the puzzle to be able to use highly nonlinear implicit numerics, because users are kind of put off by using the schemes because they're not able to. Okay, I'm almost finished. The users are not able to really close the budget very easily, but this metric gives us a way to close the budget. So it allows us to use in a practical way nonlinear schemes. Now we tested this diapiconal mixing in our model in a very simple configuration that was used by Chris Hill to test the diapiconal mixing in the MIT GCM some time ago. And this is just a channel configuration with restoring at the north boundary and differential heating and cooling at the top, and no background diffusivity. So Jean-Michel shows a lot of cases in his poster, but I'm gonna just summarize here the ones that are relevant for oceananigans. So here we have 3 cases. The first one that is a control test case that is kind of what a typical z-coordinate ocean model will use. Probably is a little bit unfair because upwind third order reconstruction is a little bit bad, and maybe z-coordinate models do better than that. But case 2 and case 3 test the influence of using high order numerics for the tracer and high order numerics for the momentum. And the bottom contours show a snapshot of a meridional velocity in the 3 cases, and also over here is clear that using a high order momentum advection gives you more resolution power. And diapiconal mixing is shown averaged in over 5 years and in the horizontal direction, the plot on the right. So undoubtedly using a high order numerical scheme for the tracer reduces diapiconal mixing, especially in the interior where where the diffusivity is below the 1 e⁻⁵ threshold. By including a higher order momentum advection scheme, there is not too much more dipicable mixing. There is a little bit more dipicable mixing below the mix layer, so we have to investigate why this is happening, and this is probably due to the fact that the variance of the temperature gradient is lower in that region. And these were the positives. There are reasons for concern that are the increased diffusivity at the top and at the bottom. At the top probably is not really a big problem because we expect the top to be fairly mixed. So higher diffusivity does not really mean much. But the problem is at the bottom, because if we start mixing at the bottom, it's difficult to recover from that. So we're trying to figure out what's happening at the bottom of our simulation. Okay, so moving forward, what we're trying to do is developing P-motion. Okay, I'll wrap up. This is our quarter-degree prototype for on a tripolar grid that where we're gonna probably develop an OMDP. Thank you very much.
Yeah, well, thank you for a very nice talk. Questions? Right up.
One online.
There's one online. Okay. Should we start with the online one then, while the microphone gets up to the. Mark Peterson, you have a question? Hello. Okay, we had I think the first question was.
PCR goes first.
Thanks for the talk. And like you said, there's been a lot of conversation about GPUs and how to GPUify this. One question I had for you, which is maybe and maybe folks from LANL and E3SM can comment too, but in a lot of ways, the computational aspect and the advantage we gain by GPUs is kind of sort of riding on the coattails of ML, right? And so the trends and like we're at this nice intersection where ML and computational science are kind of overlapping in their needs and requirements, but the trends for ML, right, are going in potentially different directions, like lower precision, tensor cores, like that kind of thing. So I guess, yeah, like what are the risks inherent in thinking about GPUifying codes and like the lifetime that you guys have considered in terms of how far, if you project like, GPU development or something like that, like how whether this is also a sustainable thing, because we've heard a lot that CPU may not be, sustainable as well. So just that kind of question.
Yeah. So when it comes to lower precision, like we're not really ready yet to do that switch, but there are a lot of atmospheric codes that run a lower precision, so to demonstrate that is possible. You have to do some kind of tricks with the numerics. You have to make sure that the order of operation is correct. You have to make sure that maybe do some stochastic rounding to make sure that you're not destroying the information in your model. We're not ready for that thing yet. But I mean, GPUs have demonstrated already that they are much faster than CPUs. So we're not talking here about a factor of 2. We're talking about a factor like 50, 100. So that is kind of difficult to ignore, in my opinion. As you said, machine learning was really powered by GPUs. Without GPUs, you couldn't have had machine learning, I guess. And I think the same advancement can be, GPUs can power the same advancement in ocean modeling, in my opinion.
Yeah, no. Okay, one more very quick question, then we have to move on. Keith.
I'm not sure if it'll be quick or not, but you can make a brief answer perhaps. Is your Wino scheme multidimensional, or are you doing spatial splitting? And if it's the latter, do the splitting errors compromise using a higher order one-dimensional schemes?
So formally, we're second order. The truncation error is lower. The prefactor of the truncation error is lower, but formally we're second order because we have a staggered grid and we're doing one-dimensional reconstruction. Now we do some kind of tricks we do different order reconstructions for different quantities. That for sure, because we see there's a trade-off in how high order you wanna have in certain variables, and what is the computational cost of that. We tried implementing a multidimensional stencil, so 2D reconstruction. We didn't really see a difference on a lat long grid. Probably that will make a difference on more complicated grids like that have like a cube sphere, for example. We're not, still not sure about that. Yeah.
All right. Thank you again. Okay, so our next speaker is Steve Griffies. He's going to be talking about rapid thermal equilibration under PI control forcing in a mesoscale dominant climate model. So, Steve.
Sure, for you.
15 minutes.
Okay, I'll be sure to
17 minutes.
ignore you, like everybody else. All right, thank you. Stephen Griffies, Princeton, and GFDL, with lots of collaborators, which we will see, talking about some of our new ocean climate coupled simulations with a model called CM4X, inspired by another thing that's called X. It was supposed to be a joke. Next. So it's a hierarchy of models, two, not a big hierarchy. Both of them eddy permitting, eddy rich, whatever, inspired by some work we did with about 10 years ago. Adele Morrison, nice figure at the top right. Some work, Southern Ocean, Veronica Tamsin, and what we call CM2O, not X, but O hierarchy with CM 2.6. So this is a plug for running, just like what we saw from Simone, hierarchies of models. And this are all coupled climate models. So this is the high-end sort of stuff, this stuff with the full bells and whistles for doing climate. Not Earth system, there's no biogeochemistry in this stuff I'm going to show. And I want to remind you of some of the reasons that I think we're doing pretty well with this new configuration and review some of the stuff I talked about 4 years ago at the this Commodore meeting. Some of us in the audience are there in this picture. This is at the museum in Hamburg. And the thing that I think is really critical is the work that really Bob and Alistair have done with vertical coordinates for the past, well, Bob since 1995, with layered models. And so I'm a relatively recent convert to the layered approach. 10 years ago, I guess I started thinking seriously about it. And the three of us wrote a paper and just 4 years ago talking about what we do. These are not really new ideas, but there are new ideas, they're old ideas that have taken a long time. I remember coming to a meeting in this place in the mid-90s with John Dukowitz from Los Alamos talking about the vertical Lagrangian remap approach. And there was serious laughter in the audience because it was so improbable that you could actually do that. And it took a long time. And really, it took, well, I'll show you in a minute. I want to make a plug for thinking about what the word Lagrangian comes from. This is a history talk here, a history slide here. We're all familiar with the notion of Eulerian and Lagrangian. Eulerian, you fix your grid and you let the flow go through it. Lagrangian, you follow the fluid. This is just basic fluid mechanics. This is Mr. Euler, and this is Mr. Lagrange. Euler with the rag, Lagrange with the sad-looking eyes. It took this guy. You probably can read that, but Truesdell, he wrote a brilliant book on the kinematics of vorticity in the mid-50s, huge footnotes on almost every page, one of which clarifies the history. It was really Lagrange that invented Lagrange. It was really Euler that invented Lagrangian fluid mechanics. It was a misreferencing subsequently. Of course, they didn't have Google at the time to really know who did what, but it's just an interesting, Euler was really the god of mathematical physics of that era. You know, Lagrange was brilliant too, but it's an interesting thing. We should be calling these Eulerian and Eulerian 1 and Eulerian 2, in my opinion. So what is this vertical Lagrangian remapping method? So this is the three-dimensional approach. It's easier to just draw it here in 3D. You take a piece of fluid, just have a rectangle or a square, you lay down a grid, you let the fluid evolve, the grid moves with the fluid. And then you have a regrid step. I have an optional statement here. If it's a laminar flow, you might not need to even regrid, but typically flows are turbulent and things are moving around. So you have to regrid, you have to renormalize or redo something to get the grid back in an organized context with the fluid that's moving all around. And that regrid step is where mixing comes in, spurious mixing, for example. But that's really it in a nutshell. The regrid step, Spencer mentioned yesterday, is not supposed to change the state of the fluid. Okay? And that, when I first started thinking about this, I didn't really appreciate that. And that simple picture, I think, really sums up a lot of what's going on in these fancy new schemes. We do it only in the vertical, and this is, you know, Rainer Bleck and pioneered this stuff 20 years ago, 22 years ago in a paper in ocean modeling. And Bob and Alistair and I think, and Eric and others had a nice dinner with Rainer, 80th birthday at Ocean Sciences. And really, we had a little session for him with just celebrating his accomplishments. And a lot of everything, a lot of the stuff that's going on in the field in vertical mapping and vertical Lagrangian approach starts from his work. There's some of the properties, there's no CFL associated with the vertical. That's really big because a lot of models are CFL bound in the vertical. You can have infinitesimally thin, no CFL. Zero vertical advection, but non-zero horizontal advection. So we have still the fixed horizontal grids. Vertical transport is realized by remapping. It's mathematically identical to advection, but it's numerically incredibly distinct. We're only doing the vertical, as I said, not 3D. The 3D problem has been done in the BOM literature, and it's not something that we think is really useful to do in the ocean. And it's pioneered by Rainer Bleck. HiCom development today has been merged largely with Model 6, so there's a lot of overlap with the different kernels. So why do we do it? So for climate problem, this is from Alistair's paper from 2019, looking at the horizontally averaged vertical time series of heat or temperature in a model run with core forcing with 5 cycles and looking at the drift. Z star in the bottom, hybrid sort of a la HiCom vertical coordinate in the top. So this was a big deal. We started developing this model, being very humble, thinking we should just develop the Z star. And then we just did this switch, and voila, it was a much different drift. And the inference is that the drift was due to spurious mixing. So that's the thing, that the diagnostics that Simone was talking about can be important to get rid of spurious dipycno mixing. So did I say everything here? There's a caveat with all these fancy things. This method, the method is not trivial. It takes some time to get used to. But I say that we've had some real smart postdocs that probe the diagnostics. We saw something from Graham and Spencer thinking about how to look at this model. And I think it's getting more mature. Just like any new tool, it takes time to get used to it for the community. So I think that over time, we'll get used to these vertical Lagrangian remapping tools. So if you want to understand a lot of the physics and math of this, you can read this paper. I love this quote. It's probably a it's not exactly a quote, but the ocean has no sides, so that some numerical models do. This is Bob explaining this. It was at a party I was not at. And I think that's Alistair. Is that right? Your dad. You know, looking at, this is the side, right? So it's I don't know. You must have taken the picture, Bob, Alistair. Anyway. If you want to understand some of what's going on from a methodological mathematical physics perspective, that's a paper to take a look at. So now the CM4X takes a village. This is the group of people started in COVID, a short project that turned out to be still ongoing. Papers are being internally reviewed now, part 1 and 2, talking about this stuff. Principles of model development that were hit hard on us. And I think all of us that know about model development, these are not new, but for those that are young, Hofstadter's law. This is a real law from a computer science guy, Hofstadter. It takes longer than you expect, even when accounting for Hofstadter's law. Remember that. Hallberg's principle. This is the Bob Hallberg here. Ocean models are Murphy law machines. Anything that can go wrong will go wrong in at least convenient time. So 6 months became, 5 years, 4 years. Keep that in mind when you're taking on a new project. Like, I'm sure that all the Oceananigans people know this. So the two models, CM4X, we have an 1/8 degree and a 1/4 degree. This is just some picture of the sea surface height. 75 hybrid layers, 1/4 degree and 1/8 degree, no mesoscale eddy closures. I don't know why it's pink there. Sub-mesoscale closure for mixed layer processes. We're focusing this grid space and hierarchy. Everything else is the same. Atmosphere is the same. Everything's the same except for the horizontal grid. Looking at the representation of the dynamics. We have no mesoscale parameterizations, sort of like Oceananigans. Not that we are at a 12th degree, but we still want to see what we're doing. We've run this model for the CM4, the 1/4 degree, 1,000-year pi control, pre-industrial control, and a historical 1850 and an SSP 585 for the CMIP6 protocol. The 1/8 degree, 400-year pi control, and still running, same historical and 2015 to 2100. So what do we get? Well, this is an SST map with a lot of blobs on it that look like we're not doing a good job. But if you're a coupled modeler, this is a darn good job, even with the biases in the North Atlantic. We've not done better at GFDL than the 8th degree. It's about a 20% reduction in the overall biases than the quarter degree. A lot of the biases are, we can point to the clouds and stuff, especially off Africa, but the Gulf Stream and the North Atlantic are clearly weaknesses in our ocean. But the Southern Ocean looks pretty darn good. A lot of models have a very warm Southern Ocean. These models don't. Yes. So the big thing here, the spin up. This is really what I want to focus on in the last part of the talk. These pi controls are essential for doing climate modeling with CMIP. You run these models out, you want to spin them up as much as you can to get to thermal equilibrium, and then call it a day. Then you do historical and your SSP, whatever, your scenarios. This 8th degree model takes about 150 years and is pretty rock solid. Cooler ocean for the remainder of the simulation. The other models gradually or quickly warm. The two quickest ones are the old model based on MOM 5, SEAM 2.5, 2.6. The red is the SEAM 4.0, the precursor to the SEAM 4X with a different atmosphere. And the green and the blue are the new models. Now, why is the new model 8th degree not warming as much as the quarter degree? The hypothesis based on some earlier work is that it's the mesoscale eddies. Mesoscale eddies provide a throttle or they keep the heat from going down just from the spin up. They reduce your and with the reduced diapicnal mixing. That's part of the thing that's really important. What else is there to say on this slide? Yeah, the thing that's really cool about this model, Lorzano, who's not here anymore, wrote a paper in 2019. Don't touch the screen. I'm not touching the screen. But yeah, I know we have the same sort of, we used to have the same sort of thing at Princeton GFDL. That's why you have this thing here. It's not far enough back. She says that we have about 400 zettajoules of heat that global warming has caused the ocean to absorb. And that's about as much heat as we burp out with this simulation within 150 years. And then it stays cool. Clearly, the green line is taking longer, and the green line is warming to an 1850 equilibrium, warmer than present day. So that's clearly, all these warming models are wrong models. Okay, but nonetheless, when you're doing climate simulations, you get this warm, you remove the background pi control when you do your scenario or historical, and most people don't worry about these details. They just run with it. If you are an oceanographer that wants to look at the interior of an ocean simulation, of the ocean in these CMIP simulations, having a model that doesn't drift very much and that's cooler than present day, at least in the pi control, is very useful. I can tell you, being on OMIP panels and stuff like that and talking about CMIP, it's like pulling teeth sometimes to get oceanographers to look at these CMIP models because they don't look like the ocean. So that's why, the pi control is a central experiment performed for all CMIP models. Thousands of years of spin-ups, huge amount of computational energy and wall clock time. There's a lot of, we're worrying about carbon footprint of our models, and it's important to note that when you're spinning these models up, that's energy that you're using to do that. And if you can reduce that, if you can make the models faster, less energy consumption, that's good. The drift to warmer present day is inconsistent with ocean measurement. Few oceanographers are, okay, I've already said these things. So some climate questions seem to be robust to a drifting model. So a lot of the climate sensitivity between this quarter degree and the 8th degree are not that different. But for science questions concerned with oceanography, I claim that a low drift model is far more enticing to those who care about water masses and nonlinear transitions, such as tipping points. Okay, and if you have a real big drift model, Bob wrote a paper talking about the equation of state makes the sea level a nonlinear problem, and so you can get different thermal expansions that cause the sea level to be. Are we done? So the mesoscale dominant hypothesis is what we've sort of formulated as the sort of framing of this problem. We claim we need three things to do a spin up. Low levels of spurious numerical mixing, accurate parameterization of subgrid scale mixing like dipycnal mixing, and a high integrity mesoscale transport. Okay, I don't think we've done any of these all three of these before this model. If we can reproduce this few 100-year spin up in other models, it'll be a new regime. plus getting faster with GPUs, for example, where you don't need to run the models for thousands of years to spin them up. That's a new thing. That's pretty cool. Okay, so this is now, if I had a longer talk, the model has problems. I mean, there's a whole slide of problems. It's got a poor Gulf Stream. You've got a lot of things, but there's a lot of enticing things. It's pretty cool. And there's a whale.
Thanks, Steve. One of the slides you skipped over, I saw the word polynyas. Does getting the stratification more accurately eliminate those polynyas as far as you know?
The CM4X model has no polynyas for 1,000 years, no super polynyas. So there's a various things that could be the reason for that, one of which would be tweaking the land ice albedo. So there's a lot of sensitivity to polynyas that is unknown at this point. But we're pleased to not have those funky super polynyas that are really awkward in the CM 4.0 model.
Thanks. I'm just curious. I mean, having a model that equilibrates more rapidly on its face is not necessarily a good thing, right? If you're short-circuiting long timescales, is it the argument here that if you're initializing with observations, that maybe the model attractor is somehow closer to that of the observation, since you just don't see this initial shock or drift, or do you think that some of these processes are happening faster for some reason?
We're not engaged in the deep ocean with spurious mixing or poorly parameterized dipycno mixing. Most of the heat that went in from anthropogenic warming is in the upper 1,500 meters or so, right? And so to burp out that heat, to go back to 1850, you don't necessarily need to engage the deep North Pacific. That's the idea. The Pacific and the Indian Oceans in this model drift very little, and the Pacific in particular is the largest ocean in the planet. So if you don't have that deep ocean engaged, you're not going to take the 1,000 years or so to spin that model up. Does that make sense? You look skeptical.
Yeah, I mean, I guess I can see that, yeah, maybe you don't want to tap into long timescales of the deep ocean, but also if you haven't initialized the deep ocean correctly, then maybe you would want to as part of spinning up your model.
Fair enough.
Okay.
But what do you, I mean, you know that you're going to spin up to that, to what's the 1850 deep ocean? If you don't, let's have that conversation later, yeah.
Okay, thank you. Thanks, Steve. Okay, so our next speaker is Eric Chassignet, and he is going to be talking about high-resolution North Atlantic Ocean modelling, impact of bathymetry, tides, and atmospheric force.
You don't want to put your hands in?
All right, so we have heard a lot about Gulf Stream and separation. So I'm going to talk a little bit about the impact of high resolution on the North Atlantic Ocean modeling. So a little bit of history, since, Steve mentioned Rainer Black. So about 25 years ago, Rainer started to work with computer scientists at the University of Minnesota and moved the MICOM code at that time from vector computers to parallel computing. And that would allow to do the first 1/12 degree simulation. And what it showed is for the first time, something that looked a little more like observations. So that's work that the student Alfonso Paiva worked in 1999. But that was made possible because of the collaboration with computer scientists, and with the advent of GPUs, again, we may be able to go to the next level. So why the improvement at 1/10 of a degree? I mean, what's been surmised is that now it's eddy permitting, therefore you have good representation of the Barclay instability process, and also that the flows are able to be inertial enough, exceed a critical Reynolds number that allows the jet to actually separate from the coast. We wrote several, here's Rainer. It's a good timing. So But identifying the, the dynamics between, the separation has been really challenging, especially doesn't work equally well in all models. I mean, I remember Frank spending a lot of time making this happen properly in POP and then putting it in the global, from the regional to the global, didn't work anymore. So one of the things we kept doing is just, let's try to see if we can quantify the value added by increasing the resolution. So went 125 to 125. So that was done using a regional model. So you have, closed boundaries, relaxation to observation north and south, from 28 south to 80 north. And one point I'd like to make is that when we switched from 125th to 150th, we kept the same viscosity. All right, so just, oops. Okay, it's pretty, it should be moving. So the main point about, running at 150th degree is that you see a current jet that penetrates all the way to the interior and say coherent. So if you look at the mean sea surface height mean, and it's a little challenging. The traditional 1/12th degree, like the first slide I showed, you have a proper separation, but the jet does not penetrate in the interior. It started to meander, form eddies and everything. So when we increase to 1/25th, you don't really see a significant improvement. You could almost argue that there is a degradation with an inertial with a recirculation south of Cape Hatteras. Only when we switch to 150th, you start to see a mean sea surface height. Those are all 20-year integration. You're looking at the last 5 years that start to resemble the observations. So here is the equivalent sea surface height variability or the eddy kinetic energy. 1/12 degrees confined to the separation, 1/25 even more, and stops at the New England seamount. And when you switch 150th, you start to have something that resembles, at least. So the main point is that there is a possible regime shift when we go to 150th degree, where what we did is we kept the same viscosity, same parameters going from 1/25th to 150th. So the only thing we change is the ability for sub-mesoscale features or eddies to arise in that simulation. And therefore that the possible inversity cascade or anyway, that the sub-mesoscale eddies are able to intensify the mesoscale, the mid-latitude jet, and increase its penetration eastward. Anyway, that's something we published a few years back, but there are quite a few discrepancies that we see when you compare to the observations. So, when you look at the EKE, you see that you have a lot more EKE in the 150th degree simulation around the New England seamount. So one of the things that we did, we kept the bathymetry going from 1/12 to 1/25 to 1/5 is the same. So it's a 6-kilometer bathymetry. What we did is say, okay, let's rerun that simulation to be more accurate and use 1.5-kilometer bathymetry. And really, we did not expect any significant difference, but it's very big. So we try and start to investigate a little bit more, so you can see suddenly that the excess EKE around the New England seamount chain was reduced. So what is it that you see? On the bottom left, you see the difference in topography in the bathymetry. And mostly it's around the New England seamount. It's pretty flat everywhere. But you have a few that exceed a few hundred meters. And here is a cross-section here. So what you see is just that when you have the high bathymetry, the seamounts are a little bit taller and just a little bit thinner. So we also did an experiment where we shaved fully the New England seamount. And what you see is that the kinetic energy is, so the jet does not meander, it's very tight, and it's only further downstream in around 60 that you start to have the the flow becoming wider. On the other hand, when you have the coarse bathymetry, the jet fills the New England seamount. You have a lot of more variability ahead of seamount, and it's only when you have the fine bathymetry that it starts to resemble, again, the observations. So clear impact of the New England seamount chain on the pathway, and we performed some idealized studies. So in the channel, prescribed jet inflow, and put some seamounts. Here's just a very short movie to show you a little bit the setup. And without going into details, the difference in the surface signature of the EKE, this is a two-layer system. On the bottom right is two very narrow seamount, like needles, and they are slightly together on the top right, and then fatter and shorter on the left. And the message is that on the this panel here, you see that the EKE is slightly more confined around the seamount. So the assumption is that narrow seamounts, less impact on the upper layer jet, therefore increase stability. So what we did is also went back to our 150-degree simulation without seamount and coarse bathymetry and fine bathymetry, and performed a linear QG and computed eigenvalue problem to compute the Barclay and stability growth rate. And what you can see is that when you have no New England seamount, it's very low. It's bigger when you have a coarse, and in between when you have a fine bathymetry. So proper representation of fine scale structure has a much profound impact than we expected. Just a very subtle change in the bathymetry had a surface, an important surface signature. So I think that's, when we keep talking about higher horizontal resolution, we often think about resolving the mesoscale or the submesoscale, but the other impact is that you have a much, much better bathymetry. So it plays a role in the overflow in the Gulf of Mexico, for example. If you have the bathymetry downstream of Cozumel, you start to generate very small cyclonic eddies that actually have an impact on the large-scale simulation. So there are many examples on those lines. So the other one is that even, sure, we have a significant improvement, but if you keep looking at it more closely, you keep seeing that you have a lot of field EKE, a little bit south of the Gulf Stream when you compare to the observations. So in this simulation on the right, the viscosity was the same between the 125th and 150th. So we did not decrease it. So then I'd like to bring up a little bit the fact that all those simulations were performed with absolute wind forcing, meaning that when the wind stress is computed, the shear between the ocean current and the atmospheric wind is not taken into account. So that's what we've been traditionally been doing in those simulations, because the level of EKE is always less than what is observed. But now, with the 150th degree, we reach a 50 centimeter square that was mentioned before. That is equivalent to the observations. So we have the ability to play with that effect. We know that the rotative wind introduced about a 30% reduction in kinetic energy through the eddy killing effect that the builder were first documented in the 80s. So Lionel Renaud, back in 2019, proposed when you used a forced ocean model forced by prescribed atmospheric fields, is that you don't have to have any feedback from the ocean onto the atmosphere. Therefore, that modifies the wind stress. So he proposed a parameterization. One of them is to use a 70% relative wind stress formulation to take into account that feedback. So, but one of the also is that if you have an eddy killing effect, that allows you also to reduce the viscosity that you actually use in the model explicitly, because it's another sink. So what we were able to do in this case is to decrease the viscosity in the 1/50th degree according to the, the grid spacing. And then, so at the end, we end up with a simulation that has relative wind forcing, but with a level of EKE that is similar in both simulation. And again, what you see is that here you see the, so on the bottom, you still see a lot of more, you see a difference on how clean the separation is as well as the penetration. And that's something that Lionel Renaud also reported using a coupled fine high resolution ROMS simulation. And now if you look at the EKE, you see now that it is significantly reduced south of the Gulf Stream. And again, a significant improvement compared to the observation. So relative wind, reducing the viscosity together with implementing the 70% relative wind, as in Renaud, not only maintained the overall kinetic energy, but also reduced the excessive EKE in the Gulf Stream. So summary, fine scale bathymetry is, does matter and will always matter. And then that some improvements by using relative atmospheric forcing also has a strong impact on the circulation. I mean, it's not something new. I mean, Lionel Renaud has mentioned that, especially in the Agassiz current retroflexion, also it has a significant impact. So, thank you.
Thank you. Okay, start with Bob.
Thank you, Eric, for that homage to Rainer Black. Welcome, Rainer. So
Rainer, for background, also Steve Griffies.
And Steve had a great homage. So your timing was impeccable, which is why the applause. Welcome, Rainer. So one of the interesting consequences is you might say that if you can't afford to run a 50th of a degree model, you might want to go back and reconsider how we're setting up the seamount chain. So instead of just naively averaging, you might deliberately choose to subsample the seamount chain so that the spacing between the seamounts is representable by the dynamics, analogously to what happens at higher resolution. Is that a direction that we should be exploring?
It's an interesting suggestion. The other one I'll talk a little bit more about tomorrow for those who are going to be around is also the use of higher order advection scheme.
So this is just following up our whatever twisted pine conversation last night. So I have actually a comment and a question perhaps. I do not know, or you haven't shown yet, how these kinetic energy improvements or SSH improvements are translating into reductions in the TNS biases in the upper ocean. So that's what we were discussing yesterday. And as we go to higher and higher resolution, yes, these are improving, but I'm not sure exactly how they are translating into TNS improvements in the North Atlantic. I think that's what we need to look at in addition to these. The second thing is that you showed 20-year simulations, but how robust are those differences? Because I do not know what the ensemble spread is in those simulations. So that would be interesting to look at ensemble spread and the envelope of how those changes are essentially impacting with control case. If they are within the envelope, then that's one story. If they're outside the envelope, then that's another story.
So what kind of ensemble would you suggest?
Well, if you run the same, whatever, 20-year simulation with perturbations, or if you can run them long, because these are probably producing internal variability in any case, how are the spreads are actually evolving in time and they are overlapping or not? That would be another metric to look at.
So we've run many with different vertical resolution tides and other thing. And I mean, that's a very small sample, but and shorter time, but they all remain pretty stable, at least within the small amount of simulation we have. Arnie? Yeah.
I also have two comments or questions. So your conclusion is to use always the highest bathymetric product that is available for your resolution?
The highest bathymetry, you mean?
Yeah, the highest bathymetry that you then interpolate onto your grid.
Yes.
Okay.
Yeah. So the way we do it is we do, we use a 9-point smoother twice to make sure that the grid is well.
Yeah. And the second question is, I mean, is anyone working on the roughness of bathymetry, for example, in Corsa resolved versions to introduce that?
Yes, so we have, we have in short answer, we have an SF funded project collaboration between the Naval Postgraduate School to look at the impact of the sandpaper parameterization on the simulation. So I can talk to you more in details about it.
Okay. Any more questions? Okay. All right. Thank you again, Eric. Okay, so our last talk before the break is by Soma Mishra. Sorry?
Soma Mishra.
Okay, sorry. Sensitivity of cyclone-produced ocean mixing to the Langmuir turbulence, a modelling study.
Hello everyone, a very good morning to you all. My name is Soma Mishra. I am working as a PhD student in Indian Institute of Tropical Meteorology with my guides Dr. Fani Murali Krishna and Dr. Anand Parekh. Today I will be talking about sensitivity of cyclone produced ocean mixing to the Langmuir turbulence, a modeling study. So tropical cyclones are a very common event in the all over the global oceans, and every year North Indian Ocean is experiencing some of the very devastating cyclones. And as cyclone is involving very high winds, so that time wind wave current and wind current interactions are more. And due to these more interactions, the surface driven wave effects are also more. And on the surface driven wave effects, the Langmuir turbulence is playing the maximum role in the upper ocean vertical mixing, as these are this is enhancing, so the vertical mixing is also enhanced through these processes. So due to this enhanced vertical mixing, the ARC coupled processes are also getting changed during the tropical cyclone times. So in the ocean general circulation models, most of the models are taking K-profile parameterization as their vertical mixing scheme. I have used here MOM5 ocean model for my entire study. And in this, the K-profile parameterization is being used to model the turbulent fluxes. In the K-profile parameterization, it has many advantages and it has many disadvantages as well. So it has the advantage that it can solve the upper ocean mixing, it can solve the oceanic mixing from top to bottom ocean layer, and it gives good result in tropics and extratropics. And also it has the best implementation in that it can represent the physical processes in a more better way. So, but it has some of the disadvantages. It has the disadvantage of taking the wave break means wave effects into account. So, and also it has means in MOM5 with K profile parameterization, it is showing the surface colder bias and subsurface warmer bias. So to account for these biases, how to deal with these means how to reduce these biases. So my goal is to implement and in the K profile parameterization, it is used to model the turbulent fluxes, and here this K term is the diffusivity for scalar or viscosity for momentum, and this K term is involving into the product of the boundary layer depth, the vertical velocity scale, with that the shape function. Here this shape function is taken as the cubic polynomial which is involving of the 4 coefficients A0, A1, A2, A3, which is with the 4 boundary conditions given by O'Brien. And studies are saying that this third order cubic polynomial is not sufficient for accounting means for taking into account the wave driven processes. So for that, Core et al 2021 has one study that if we revise this shape function with a 6th order polynomial, then we may take into account that Langmuir turbulence in a more better way. And also previous studies are saying that W means only taking care of that G sigma is may not be sufficient. So we have to look into that W scale profile as well as with that the G sigma profile. So for this G sigma, I have used the Core et al scheme, and his scheme he has implemented in LES simulation studies. So this scheme, this last polynomial, it is the Core et al given polynomial 2021. This I have implemented inside MOM5 model, and also with that the vertical velocity scale. This is the Smith et al scheme 2002. This I have implemented in the MOM5 model. So then I have run the MOM5 model, 2 runs. Control is with the previous that cubic polynomial shape function control run, and experiment is with revised shape function and the vertical velocity scale. So I have run with quarter degree means 0.25 degree horizontal resolution, 50 vertical levels are there, and spin up is done with core climatological forcing, and I have run with JRA 55 do forcing. And then I have validated those data, means I have compared those data sets with respect to Argo 10 days averaged 1 degree horizontal resolution data and Ramabui daily data. So the outputs I have analyzed some of the vertical profiles of temperature, density, CR, stratification and all, some spatial distribution of SST and subsurface temperature, and time series of oceanic heat content and subsurface temperature. So as my study is involving for the cyclone times, so I have analyzed the 18 cyclones from 2008 to 2019 and 15 are in eastern part of the Bay of means eastern part of the Indian Ocean, that is in the Bay of Bengal, and 3 are in Arabian Sea, that is western part. And these blue circles are showing the Ramabui locations in the Indian Ocean. The right side I have shown, right panel, I have shown the observed and forced wind speeds. So A is showing the Ramabui wind speeds and B is showing the JRA 55 wind, and this is from the prior to the 5 days to the front 5 days. 0th is the closest to the buoy location. This I have shown because I want to see that whether model is properly forced with the JRA 55 do forcing. That means it is the cyclone induced winds are going to the model. For that I have shown this. So then what I get, the upper panel is showing for the temperature and the bottom panel is showing for the density. And leftmost panel is showing the control bias, middle is the experiment bias, right side is the bias difference from the experiment to the control. And these are for, I have analyzed for all the cyclone cases, and the dark line means the black line, black dark line is the mean of all the cases. So we can see that case to case improvements are there, and also with respect to mean, improvements are there. In the subsurface, it is improving 30 to 40% temperature bias, and in the surface, though the bias is very less in the surface colder bias, but it is improving up to 60 to 70%. As well as in the density profiles also, it is improving the subsurface density by 0.2 kg per meter cube. So these results are supported by the RMSE profiles. These are the mean RMSE profiles from control experiment and from the experiment. So blue line is the experiment and red line is the control. So from here also we can see that with means the subsurface temperature and the subsurface density, both biases are improved, means both RMSEs are improved for both the cases in the subsurface. So the upper panel is showing the stratification profile. The upper ocean means A is showing the control bias, B is showing the experiment bias, and C is showing the bias difference from the experiment to the control. And it is showing the black lines are same as mean line for all the cyclones. And it is showing that from the control to the experiment, the biases are improved in the upper ocean. And also I have checked the RMSE, means vertical integration of heat, how it is behaving. The oceanic heat content I have taken the time series and the subsurface temperature time series. The red line is showing the subsurface temperature time series, and the black line is showing the oceanic heat content time series. Zero line is showing, means the 0th point is the closest to the buoy location from 5 days prior to the 5 days front. So it is showing that temperature is improved, means temperature RMSE is being improved by 0.8 degrees centigrade, and the OHC means the vertical integration of heat, that is also improved by 0.003 into 10 to the power 10. So now these are the means vertical structures and integrated structure. Now how is the spatial distribution? For that I have analyzed the right part of the Indian Ocean, that is in the Bay of Bengal, for two extreme cyclone cases, that is cyclone Fetai in 2018 and cyclone Kayar in 2019. The upper panel is showing for the Bay of Bengal, and the lower panel is showing for the Arabian Sea, and both the cases we can see the improvements. The leftmost panel is showing the control bias, middle is showing the experiment bias, and right is showing the bias difference from the experiment to the control. So we can see the experiment, the bias, the control bias was there 0.8 degrees centigrade, which is reduced by 0.4 degrees centigrade. In the Arabian Sea, means in the F box, we can see the improvement has happened mostly. So then how is the subsurface temperature? So the same thing I have done for 100 meter temperature, and it is showing the 2 degree bias improvement is happening from the control to the experiment in the Arabian Sea. And this is also same, the left is control bias, middle is experiment bias, and right is the bias difference from experiment to the control. So this is my CR profile. CR bias I have not shown because there is no available daily data sets. These all are, I have explained, means I have analyzed daily data sets. So no daily data sets is available in our ocean. So that's why this is the CR profile from the control to the experiment. We can see if we take the modulus values, we can see that CR is being improved, CR is being decreased from the control to the experiment in the upper 25 meter, then it has been increased. So this is the vertical profiles of diffusivity and viscosity. Left panel is showing the K profile for the momentum, and right is showing the K profile for the scalar, means tracer quantity. So The middle boxes are showing with respect to the logarithmic profiles I have analyzed, and these are the profiles. So this is the left is showing the shape function, whatever I have changed. Again, this middle box is with respect to the logarithmic scale. From blue line is for the experiment, and red line is for the control. And right side it is showing the W scale profiles. Left side is for the momentum, right side is for the scalar fields. So now I want to conclude my study with that. I have changed the shape function and the vertical velocity scale inside the model, means inside the KPP in MOM5, so that with that the stratification and shear is also getting changed, so that we can say the buoyancy driven mixing and the mechanical mixing both are changed, means both are shaping in line, and through that the thermohaline structure is getting changed, means thermohaline structure biases are getting reduced. So for simulating more proper way, and this is because of we are taking into account the Langmuir turbulence, the wave driven processes more perfectly according to Coretal scheme from LES. So to better simulate the thermohaline structure during the North Indian Ocean cyclone time, this revised KPP formulation may be useful. So now I want to acknowledge convener of OMDP Commodore Workshop 2024 for accepting to present this research work, WMO and Cliver for all the travel and other supports, IITM Pune for funding me research grant, both of my guides for thoroughly supervising me, and then thank you.
Thank you. Questions for Soma?
Very nice talk. Thank you. I wanted to ask, okay, so the premise is that I think there's this idea out there that Langmuir turbulence, Langmuir effects generally tend to enhance mixing.
Yes.
And so I think in the slide at the end, you were showing reduced viscosities and diffusivities in the experiment run relative to the control. Was I understanding that right? Were you showing actually suppressed viscosities and diffusivities in the boundary layer associated with Langmuir effects, these parameterizations?
No, these are improved.
Oh, it's the other way around. Okay, I'm confused. Thank you. Maybe flip one forward, back. No, back the other way. No, yeah, sorry, I'm confused. Never mind.
Thank you for the study. You've examined the structure of the boundary layer mixing under the cyclones and found significant improvements. KPP also has interior shear mixing when the shear-Richardson number becomes quite small, and a cyclone, of course, is a case that can have very intense shears. Do you think there are prospects for even further improvements by reconsidering the details of how the interior shear mixing piece of KPP is being handled in cases under hurricanes where you have very intense shears?
Thank you, sir, for your question. And you are asking about the bottom boundary layer mixing, the interior ocean mixing. That I need to check because there is no shape function and other things are playing role. So.
Any other questions? Okay. Thank you.
Thanks for the talk. My question is, obviously cyclones have very extreme winds, like Bob was saying, right? But we also have events, katabatic winds coming off of Antarctica, right? That have super intense things. So I think my question to you is, how specific are your results and conclusions about, the sensitivity of KPP to these kind of extreme wind situations, to other situations outside of just like the cyclone eras, and how does it generalize to the broader ocean?
Thank you for your question. Actually, I have checked these results for all over the tropical Indian Ocean also, and this manuscript I have written, and that is in process. So that is also tested for the whole tropical Indian Ocean. It is behaving more or less like this. Thank you.
Okay, well, I think we have a break now until 10:30. Okay. Thank you. Very nice talk. I'm sorry I got your name wrong at the start. I did know it was Soma. Did I say so? What did I say incorrectly?
Okay, I'm going to talk about the Equatorial Pacific Cold Tongue. It's a region of leading significance for global climate dynamics and prediction, as I'm sure you all know. The plot here is just showing a climatological air sea heat flux, highlighting the cold tongue is hotspot of high, the most important regional hotspot of mean heat uptake by the ocean circulation. It's also the center of action of El Nino. It's key to seasonal to interannual prediction of climate system. As Gokhan has been talking about, persistent biases, the cold tongue biases still persist. For example, in CESM2, two strong zonal SST gradients in that case, 2 week stratification in the top 50 to 100 meters, two strong stratification 100 to 200 meters. There's some papers there you can look at. And there's some evidence that mesoscale to turbulent scale processes are important and potentially key to improve simulations. Okay, so I'll try to make the case a little bit for that last point. And it's going to be a comparison here between some high resolution mesoscale resolving ocean simulations and observations of mixing. So the plot here on the left is a time series of the seasonal cycle of SST in black in the like 0 north, 140 west in the middle of that equatorial Pacific cold tongue. The red is the surface heat flux. The blue is a turbulent heat flux at the bottom of the mixed layer. And you see there's a seasonal cycle where the heat flux is above the cooling associated with mixing, taking heat down in the early part of the year, and you have that red area. So you net warming, that's the SST rises. And then in the boreal autumn, you see the mixing is strong relative heat flux, and you see the SST goes down. The argument here was that mixings play a very important role in driving the seasonal cycle in this region. Okay, so here's a nice result from Anna Deppenmeyer from the POP2 nominal 10th degree global ocean configuration. It shows a very qualitatively similar thing. You have the seasonal cycle on the x-axis, SST rises and falls as we'd expect, but the heat flux is a little higher than this observational estimate over here, and the mixing is a little bit higher and different qualitatively. So those are pretty large values, right? The heat fluxes we're talking about, both with mixing and the surface, are sort of order 100 watts per square meter. No, touch that. So just for comparison, here's another ocean model. Happens to be in a paper that I wrote, which is why it's here. This is MIT GCM. It's a regional configuration at 5 kilometer nominal 20th of a degree resolution. It's forced by GLORIES 12 reanalysis on the sides, GRA 55DO, which hopefully all these acronyms are meaningful to most of you. The y-axis is a little bit longer, but the scale is the same. So it's about 200 watts per square meter, from 0 to 200 on the left panel, 0 to 200 on the right. It's about the same range. The black curve on the right with the circles is the same as the blue curve on the left. The gray line is the MIT GCM estimate that's analogous in the climatology. The dates are not quite identical for these comparisons, but we think both are reasonable climatological estimates. The MIT GCM is 1999 to 2018 for reference. But I want to emphasize, so you can see right away that the seasonal cycle of the mixing in the upper ocean is significantly stronger in the model than in the observations. In the mixing scheme, the vertical mixing scheme is KPP. And I just want to emphasize, so the full range, every monthly mean from the 20-year simulation are those thin gray lines. So there's quite a range of variability between one month and the next, But for a significant part of the boreal spring, the mixing and observations is below every single monthly mean of the model. Hope I said that right. Do I have a timer here somewhere? Yes, I think I do. Okay. And I mentioned that mesoscale processes might be important here, right? So we're talking about vertical mixing there at this one point where we have decent observations showing that there's some discrepancies between the model and the observations in kind of a climatological sense. But what does this really look like in a snapshot? Well, we don't have observations of turbulence quantities to show how mixing varies in space, but we can look at our high resolution model, that same MIT GCM simulation I showed, and this is a map of turbulent heat flux. This is in a paper, and I want to highlight right now, Deepak Cherian has done some really nice work supporting this. This is a paper led by him and his plot. So it's showing the turbulent heat flux below the mixed layer depth. So your range is hundreds of watts per square meter there. And it's showing that it's modulated by the mesoscale tropical instability waves. So of course, the mixing, like we all know, is energetically controlled by things like winds and waves and buoyancy flux at the surface. But in this region, the structure is also controlled by the oceanic shear, which not only has your sort of undercurrent signature, that's the high mixing right along the equator, but also the modulation by the tropical instability wave shear, these tongues of high mixing going off. So it's a complex scale interaction problem, and in some ways, maybe it's appropriate that I'm in this high resolution ocean modeling session as opposed to vertical mixing. But anyway, that's a motivation. How can we deal with this problem? And it's not so easy, and I don't think we've solved the problem anyway, but here's what we tried to do. So we want to try to understand what this vertical mixing is doing, how it depends on the atmospheric forcing and the oceanic forcing. And so what we did is we embedded a large eddy simulation effectively inside this regional ocean model. Then what we're going to do is we're going to confront the parameterizations coming from the ocean model against the LES solutions as, quote, truth. And then we're also going to confront the LES against observations. So we're not going to just trust that they're true. And essentially what the LES is going to do is going to solve an equation like the top one. The first 1, 2, 3 on the right-hand side are hopefully familiar. 4, 5, and 6 are special for this case. And F is the most important one. For example, in momentum, it's the same for temperature, but analogous. This is for momentum, zonal momentum. Say you have a regional ocean model tendency terms that are forcing this situation. Coriolis is solved online by the LES, and turbulent mixing is solved online by the LES. So you don't see those terms on the right-hand side, but every other term coming from that regional model is injected as a forcing on the right-hand side. That causes the mean flow to evolve. Pressure gradient force, nonlinear terms, these are quite important and evolve on fairly short timescales in this region. There's also restoring with something like a 10-day timescale to make sure the LES mean doesn't diverge too far from the parent model state. It's not that important in this case. And keep in mind, turbulent timescales are much, much shorter than that. Okay, so can we do this? It's not so obvious that this will work. I'm going to try to show you that, yes, we can do this. This is an approach that we can use to try to understand the processes going on and parameterize them better. So this is a plot showing a time series, kind of like observations of surface heat flux and wind stress on the tops. The blue, choppy, it's like every 6 hours. They're showing you the diurnal cycle of surface heat flux. The sort of more slowly evolving curve with a sort of weekly modulation, diurnal modulation is the wind stress. It's something like 0.05 Newton per meter squared. It's not super strong, but you see these modulations, over order 1 fractions of the magnitude. And then below that is a depth time plot over 35 days, which is quite long to run an LES like this with currents of a meter per second, something like a 0.8 meter grid resolution in the horizontal. Let's think about your CFL constraints. You have time series of turbulent heat flux. You see the strong turbulence, hundreds of watts per square meter in the nighttime penetrating below the mixed layer depth in magenta. Sometimes the mixing extends at depth beyond during the daytime once the surface mixing is shoaled. So you can see these sort of deep cycle events, which I'm not going to try to do, but you can see some of these early ones mixing. There's pulses of mixing, and it kind of extends to some periods of time during the day at depth when the mixing above has shoaled. That's characteristic of this deep cycle that we see, kind of unique to this region. Below, we have the zonal current. You can see the south equatorial current at the surface going from east to west, the undercurrent coming up from west to east, creating this very, very strong shear. The temperature contours in white. You can also see the modulation of a single tropical instability wave. So it's designed to be 35 days because that's a period that's necessary to span a tropical instability wave period. You can see that in the zonal velocity of the surface, how there's this sort of roughly 1 period modulation of the zonal velocity there. Okay, and of course there's loss of modulation and mixing at different time scales. You see these weekly time scales, daily time scales, of course, are dominant, perhaps also this 30-day time scale. Okay, I said I was going to confront this against observations. These are some observations. They're not the same time. They're not the same atmospheric forcing, but the point is to show, and it's not even the same variable. This is dissipation rate of turbulent kinetic energy. The point is to show, which, as Bob showed earlier, the Osborn relation you can use to relate this thing to diffusivity and then to a heat flux if you have stratification, which is what I was showing before. But anyway, there's some vagaries with that I'm not going to get into. The point is to show that qualitatively you see these same features where you have your mixed layer depth with this diurnal cycle, these deep cycle regions of strong turbulence below the mixed layer, penetrating, you know, over this sort of 50-meter scale below the mixed layer. And it's associated with quite strong turbulence, quite strong mixing. Okay. I'm going too slow. I'll try to speed up. This is to show that the shear and stratification of the model have characteristics very similar in the LES to observations. These are some observations in the bottom panel here, showing that strong shear of the EUC, which is the dominant source of the shear in the left panel. These are, again, not the same time and location, or not the same time but the same location as the model. You have this shear squared, n squared slopes, which kind of almost linear in log space from high values at depth just above the UC core down. And then the Richardson number, gradient Richardson number, is almost fixed at about 1/4. That's very similar features you see in the model. The Richardson numbers in the top right there, you can see this median and interquartile range is just below 1/4 there. The shear squared and 4n squared are plotted on the same curve. So you can see where the Richardson number equals 1/4, where those are about the same place. I also did some analysis looking at the sort of statistics of turbulent heat flux below the surface at daily timescales. You know, as we saw earlier in that MIT GCM plot, that varies a lot from 1 month to another. These are the same time of the year, but even between years interannually, a given month may be different. But you can see the blue, compare just the blue histogram of observations to the blue histogram of the model. Those are comparable. So you see the observations were a little actually weaker turbulence, but sort of qualitatively similar. The bottom panel shows temperature frequency spectra from the tau mooring, which is aliased because it's just a 10-minute instantaneous sampling. The black curve on there is the temperature frequency spectrum from the LES, aliased in exactly the same way with 10-minute instantaneous sampling. And the 10th and 90th percentile of the spectra from tau moorings is shown there in the blue. So you can see we're near the 10 percentile, out at the tail there of 100 cycles per day. But, just sort of follows that range all the way down. We're a little low kind of at the 1 to 5 cycles per day, which is possibly consistent with missing internal waves. Okay, there's sort of just a close-up of dissipation rate, same variable. We get these kind of qualitatively similar features of the diurnal cycle. I'm going to skip this. We can do this in LES, of course, anywhere off the equator, on the equator, different latitudes, places where you don't have measurements. That's all great. But I'm going to talk a little bit finally about what we can do to use these experiments to evaluate parameterizations now and possibly improve them. And I'm going to do this through an analysis that's looking only at daily mean turbulent heat fluxes. So I'm going to take daily averages of this thing on the top. I'm also going to add the solar flux, penetrating solar flux to the turbulent heat fluxes. And so we're going to lose those blue regions of negative heat flux associated with convection of the surface because the solar is compensating that. And you have the strong mixing at depth. So that's the plot now at the bottom. It's kind of this daily mean turbulent flux plus the solar there associated with that plot above. And I'm going to look at these properties. So one of the things we can learn about this is just doing some linear regression. No fancy machine learning yet, although I'd like to play some games. We can run lots and lots of these simulations. This is like, there's something like 400 days of simulated LES time around the tropical Pacific. We can put all of it at different latitudes and longitudes on a plot and see if it relates to anything physical. this case, this is just a regression with friction velocity at the surface and a bulk measure of the shear in the ocean. And really, this is to emphasize that this turbulence gets its energy from, at the peak, below the mixed layer, gets its energy from two sources. It gets its energy from wind, and it gets its energy from the shear. And so there's an interaction that goes on here. It's not sort of, it's not something you can isolate and think of as interior mixing driven entirely by some local shear, nor is it something you can think of as we can ignore the ocean shear, all the energy comes from the wind. But if you think about these two variables together, this is kind of a shear production scaling, if you will. You can get something like that turbulent buoyancy flux within a factor of 2, the factor of 2 bars. These are all the daily means. The factor of 2 bars and then factor of 3 bars are shown off the one-to-one line there. I'm not going to get into what all the different dots are. There's also some observations on there, I should emphasize. That's the blue cross, which is actually just below the one-to-one line in terms of the significance. So those are like significance bars and where the mean is for a whole experiment, like a 30-day experiment. So there's 10,000 microstructure profiles that are going into those blue stars on there, which I think the cluster more or less is on the same, within the noise, so to speak, factor of 2 noise we expect.
Dan?
15 minutes? Okay, good. Perfect. Yes, independent microstructure observations are consistent with this story. There's somewhat less variance. I mean, we can see how much variance such a scaling can explain. All this is to motivate the point that this LES, there's some physical intuition we can pull out of this relatively quickly. And we can see if, this means we can parameterize these things if we can get this in terms of quantities that are non-turbulent that we know from an ocean model. Okay, now we're going to look at KPP. So the original model, the regional model had KPP running at the same time it was running. And the LES is on the top. The scaling derived, the parameterization derived from that scaling that I just showed is on the bottom. Not perfect. And then KPP is on the bottom. And my claim would be that KPP is significantly different from these on the above. A particularly notable issue is that you see very clearly in KPP this 30-day modulation of the TIV that you don't really see so obviously in the other two cases. Okay, so can we do better? So I think Bob Hallberg already asked me a question about this at some other meeting, but anyway, I made some changes. I just sort of, one can do a more careful analysis. One can try to optimize KPP as Bill Large did back in 1998 to match these simulations. And I just sort of have started by saying, well, let's try some changes. Those are the changes to KPP on the top. Those parameters, the bulk Richardson number of 0.3 to 0.2, a threshold Richardson number for the shear mixing scheme of 0.8 to 0.5, and a maximum viscosity nu max of 50 times to 25 times 10⁻⁴. Okay, so I'm going to just show diagnostically KPP you can diagnose on these LES outputs based on the mean conditions and then compare with the LES fluxes. So we're not going to run online first, just going to compare diagnostically. This is the LES state. There's another LES here down below at 3 north, 140 west, 0 north, 140 west. That's the one we're talking about at the top. Okay, there's KPP. Just diagnostically, left-hand parameters, these are the defaults. Way off, right? I mean, way too much mixing. KPP is not this bad in a real ocean model. This is because I'm doing it diagnostically on the LES mean states, and the gradients are different. And the diffusivities are different, and the way that equilibrates is to some flux state that's not so bad, because otherwise your SST would just go totally off the rails. Okay. We can improve the situation significantly by changing those parameters. See, look, this is the revised parameters. This can be implemented in an ocean model like MOM6 globally. Again, this is by Deepak Cherian. We can show, I'm not going to get into it, is that we can significantly improve the shear and stratification in the upper ocean by implementing this change in this region. We don't know, of course, or we do know rather, that KPP parameters for this region are probably not appropriate for the Southern Ocean or Station Papa, where those original parameters are probably better. Now, as we heard from Akash, there's probably no reason why KPP should have one set of parameters everywhere. So I think it's perfectly plausible that we might be able to take advantage of this information to develop a scheme with parameters that are appropriate for a more general set of conditions. And yeah, I'll leave it at that. I'm over time, sorry.
Thank you. We have time for one question.
You sort of blithely said, "Oh, the Richardson number is close to a quarter," but I think that remarkable thing about the simulations is that it's not a quarter. It's actually the median value is more like 0.2, and you have many values in the LES that are significantly less than 0.2. I think that's also borne out in the observations, and that's maybe you didn't say it, but maybe is the motivation for reducing these Richardson number related parameters. I think that's actually, you can never capture that kind of behavior with KPP, or actually, I'm not sure with any known parameterization, the kind of variability in the Richardson number that you're seeing. So I think it's kind of interesting. It's kind of a comment and a question, like,
Yeah.
have you thought about that?
I agree with everything you just said. Up until you can't capture that with KPP, I'm not 100% certain of that. Yes. So yes, Richardson number varies. This is like an example, just showing from the LES, like time series one, random one. It's not just sitting at 0.25. And in fact, the observations, like you say, are, if you look there, a little below a quarter, right? Both the model and the observations are a little below a quarter. What the exact value? Yeah. So, well, whatever. I'm not going to get into the semantics. We'll leave that at that.
Okay, thank you very much. All right, so that brings us to the discussion for this session. And our note taker is Luke Van Rokel. Thank you. Questions. Yeah, no, there's another. There are a lot of questions. Yeah. Yes, please. Much appreciated. Okay, so if you want to have a quick read of that. All right, should we just start with these then? Okay.
Thank you. I can. I'm interested in number 3 because I know there's efforts in Europe around unstructured grids. But it seems to me if we care about, if all we care about is eddies, unstructured grids are kind of useless because eddies are everywhere. But if we care about coastal or those interactions, maybe refining towards the coast is what we need. The benefits are tempered by the fact it's so difficult to analyse, but it seems to me if we think boundaries are really important, then unstructured grids could be very useful in the future.
Yep.
Can I just follow that up? So I don't know if you noticed, but in Eric's plots, his 50th degree model had the open ocean eddy energy right, but on the coastal shelf it was actually deficient even compared to a VISO. And so that's backing up what you're saying is we don't have the resolution on the coast, even at 50th degree.
I would like to comment on Stephen Griffies' number 4. I claim that the Oceanagans efforts have shown that they have changed the cost of calculations. I think that's a provocative piece of work that the community needs to take seriously.
I think there is also some difficulties in parameterization of the ADs that has been sometimes ignored in the sense that the time scale for biochemistry, for instance, it's comparable with the time scale of EADs. And when we think of parameterization of the EADs, we look at the mean effect in a sense. But the problem is that the biology responds to upwelling that are generated by the EADs that are going to be short. I mean, it's similar time scale. And the parameterization is going to miss a little bit this interaction due to the time scale that is not separated enough.
I have a response to what Andy just said on the unstructured grid. I'm not a modeler of unstructured grid, though. I agree with you, eddies are everywhere, and that's why we love to have resolution everywhere. But I know that, in particular, FISOM now uses grids which are motivated by the SSH variability, for example. So putting resolution exactly where eddies are in the current climate. If this is sufficient, if this helps to represent the eddy effect on a global scale, and if that is not subject to change on a changing climate is another story. But there exist certain steps to implement that.
I wanted to ask on this aspect of refining the grid exactly where you know that there's SSH variability. Aren't you constraining your model to have eddies exactly where you put resolution? So isn't that like a data simulation type of exercise? And how will that look like if the climate changes?
Yeah, as I said, I'm not an unstructured grid modeler, so that's exactly my argument there. But this is at least under the current climate, the best resolution that you can have with unstructured grid to always resolve the first power clinic gross period radius in addition.
Well, I think when it comes to, for example, the FISOM community and the structured grid, that's also just partially true because lately what we have seen, for example, in Destination Earth, when we run high resolution simulation is that in the end, in the ocean, we put high resolution everywhere. So this thing of putting the resolution only where there is the variability has been lost a bit in the last years because they realized it's, yeah, in the end with the fact that you still need to reduce the time step, it was worth having the high resolution everywhere.
Can you pass it to Andrew?
Yeah, it's interesting. The CFD community, right, uses adaptive mesh refinement pretty commonly. I think there is this question though, like, typically you do it something based on like shear or like, the stretching of the volumes or whatever. And it almost requires an unstructured like mesh, right? So you can do that online refinement. I think the question for oceans is really that question of when we run these models, we will generate turbulence everywhere. So do we actually end up getting any improvement in performance out of that, right? Because the mesh will just kind of grow to a certain size and go. So I think the question on the mesh refinement might be might be more about something, a new type of metric for where you want to refine the mesh, other than just the normal ones that CFD people normally use, if we want to try to explore that as a technique.
I always have so many. Will unstructured grids work on GPUs? This is just a naive question. Yeah? Oh, cool. Okay.
Okay, so I'd like to just tie in with a comment that Teresa made about the coastal parameterizations and the mixing session we've had. A lot of our parameterizations have been designed, that we're using in the GCM world have been designed knowing that we're averaging over a lot of scales. And I think in the CFD community and the LS community, they have very different kinds of closures designed for a different purpose. And I think Ocean Angling has taken a bit of that strategy by just having fewer conventional parameterizations from the GCM world and newer LES more like. But what I'm wondering is, if you were thinking about unstructured or if you're thinking about going to high resolution, at what point do we have to reconsider the validity of all of our known parameterizations? I mean, if you haven't got scale awareness in your vertical mixing scheme, should you be using the same coefficients? Have we just seen two examples of very different kinds of mixing? at different timescales and spatial scales. So using one parameterization across a range of resolutions seems very potentially risky. So that's a big hurdle, and I think the atmospheric community have experienced this problem, that they have had a lot of trouble with crossing regimes of resolution and using the old parameterizations.
A comment to the unstructured grids. I mean, they offer a degree of freedom of flexibility, so we can adapt, but we don't have to. I mean, we know a priori where the eddies are, so we can put the resolution there. We don't have to do it in an adaptive way. I think this is a bit too much for a current state. But putting it where we know they occur, that makes sense. And then the challenge is exactly, as Alistair said, how to adapt the closure to that. This is that might be this challenge might be to stretch the actual closures and to see how they perform. That might lead to some new insights. In general, I don't think that the unstructured grid stuff is very much different from the structures. And for me, this is becoming more and more similar. But these fitting that to boundary currents, for example, this is a new thing that we need to explore, but the rest is not fundamentally different. It gives us some new options and we should explore them.
What I was going to do.
I just wanted to comment about the gray zone. I think there's in engineering in CFD this has been tackled, like doing hybrid LES RANS stuff, and so there's a lot of approaches I think that we can borrow when we get there. But I think that in the ocean, I don't know exactly what the gray zone would be, but it's probably something like 30 meters, right? So we're far from getting to there in a global model, but close in regional. 10 to 30. 10.
So when we're talking about taking techniques from other communities, one of the things that's really unique about the oceans is we care about conservation properties for really long times compared to the intrinsic times of eddies, right? In the atmosphere, the radiative damping time might be something like a week to a month, depending on where you are. The eddy turnover time scale, maybe a few times that. So there's plenty of stuff that fixes the state of the atmosphere. In the engineering community, I don't know of any situation where people care about something of order. We care about timescales of order 1,000 years, and if we think our eddy turnover timescale is a month, we're talking about 10,000 eddy turnover timescales where we want to preserve properties. So we are a little bit unique in that very long timescale of conservation that we care about for the climate problem, and it's going to be something that is going to pop up in many cases where things that will work well in other settings simply don't apply to many of the ocean climate problems that we're trying to address.
Riffing on Hallberg, I also want to return to the reduced precision idea. We saw a couple of talks about spurious mixing, and I wonder if those that are thinking about reduced precision have any comments on the ability to maintain this 10,000 eddy time scale with dipycnol spurious mixing being really tiny. Is that something that we're going to lose if we go to reduced precision?
So there is a student of John Marshall MIT that did the test of LES using reduced precision and full 64, and apparently there is more diffusivity in the low precision, because probably with diffusive numerical schemes you have some kind of small errors that will make your solution more diffusive. So we're a little bit cautious in looking at reduced precision, but they have done it in atmospheric models. So it's probably, you have to think about it a little bit hard, I think, and make sure that everything is well consistent.
There was actually some effort at CMCC in Italy, or I can't, maybe Bologna. Is there anybody from that group? They were trying reduced precision in the ocean, I think. Okay, nobody.
Yeah, Anna from the Met Office. So CMCC, I don't know what the work has been, but ECMWF is moving towards NEMO at single precision. Barcelona Supercomputer Center has for a long time been using mixed precision. And from ECMWF, what we know, well, Lorenzo will know more. Basically, they had made the decision that for climate runs, you may need double precision, but for short-term forecasting, and that goes up to seasonal scales, you wouldn't need the double precision.
Did you want? No. So Eric wants to say,
But it's more a comment, but actually there is a question about are ocean models ready for final resolution? And there should be also a question about what are, for the external parameters, for the do we have a bathymetry at a sufficient resolution? Do we have the atmospheric forcing at a resolution that is consistent with what we resolve in our ocean model at very fine scale? So,
Yeah, I was going to actually comment on 8 as well. The sea ice modeling as well, and interaction at fine resolution has not been fully explored yet. But I'd like to go back to 7. I mean, ensemble of coarse resolution simulations. So I'm not a climate modeler, but when I look at the CMIP reports and everything, you see tons of ensemble simulations. What have we learned from comparing all those ensembles that we didn't know before, or that we can, or that we will actually learn by performing more of them? I mean, we know they are biased. We know they are biased. There have been several attempts to fix, but I think putting resources in deterministic fine resolution does teach us quite a few things.
Yes. Ensembles tell you what not to believe.
Well, that was very terse. Do you want to expand? I mean, I think there's so much usefulness with the ensembles. Like take our high-res models, the Southern Ocean biases and all that stuff. If you look at the, you can essentially run 10 ensemble members, and nature or reality is just one member of that, and you can essentially check the spread and then get the percentages or all of that information. Additional spread information is quite useful for everything, I think.
No, I understand the value of ensemble, but thought we have enough right now at coarse resolution.
Well, probably
that's what
we
I meant.
have enough. Maybe, I don't know. Yeah.
Also, to calibrate parameters, it's necessary to have ensembles of simulations. You cannot do it with just one simulation. Probably not.
We have enough.
Ah, okay, in that sense. Yeah.
Regarding, I guess, questions 5 and 6, Dan Amrein from NCAR. You know, we talked a little bit at the break about the handoff between regional climate configurations and global climate configurations and regional models, where a lot of the impacts level work is likely to be done. I have a friend who works at the Nature Conservancy, and he gets calls from governments in South America, and they say, which of the CMIP models should we use to think about ocean conditions in our economic exclusive zones over the next century? And the answer is none of them, right? But he doesn't know what to tell them because there's not an established workflow. And so it seems like in terms of how resources should be dedicated, a piece of this is, yes, towards getting a better representation of the overall climate, but also understanding what people who run meter scale models of coastal sediment transport, or coastal, what do they need from these bigger models, right? And how should we continue to prioritize those things? I feel like that we should be talking about that more.
I think I just want to say, is it Dan? Yeah, I totally agree. And it comes back to like the question of why, like, what are we trying to do? And I don't really know what the value is in working to continually improve coarse resolution CMIP models. You know, like the answer is not changing, or the important answer is not really changing.
I can give one. Well, go ahead, Bob. Sure.
It depends on what question you're asking. If you're asking what is the climate sensitivity of the planet as a whole, maybe that hasn't changed much since the Charney report. However, as we push to higher resolution, we can start to answer a wide variety of questions about the impacts of climate change in ways that are actually manifest locally. Dan, you make a really good point about regional downscaling. In the US, at least, there is a major new effort within NOAA, the Climate Ecosystems Fisheries Initiative, that involves a fairly generously funded effort at regional kind of whole coast scale modeling of all of the coasts around the US with partnerships with several other places covering East Coast, West Coast, Pan-Arctic, Central Pacific, and the Great Lakes. You've heard about some of them, including engagement with the National Marine Fisheries Service, who are the ones talking to fisher folks and the managers. So this is something that is a growing effort in the US. I'm sure there are counterparts in Europe. I know of counterpart efforts in Asia. So it is something that is being attended to at kind of a programmatic level.
Well, I was going to expand upon a little bit in response to Paul. There are certain, again, it depends upon what you want to, what the question is. There are so many applications from the paleoclimate community, and Keith here, for example, from the biogeochemistry, and you cannot really afford to run long simulations, millennial timescale or longer simulations at whatever even quarter degree resolutions. So that's why I always advocate for an hierarchical approach. We need the ultra high resolution simulations to learn from them, perhaps improve the parameterizations that we still need to use for the next 5-10 years probably at coarse resolution. And that comes back to my arguments yesterday that we need to still address the persistent model biases at coarse resolution. When I say coarse resolution, 2/3 or whatever quarter degree, because there are still quite important scientific problems that need to be solved using those simulations.
I would, yeah, so sort of following on from Gökhan and also sort of addressing Paul's comment, I don't think it's true that there's nothing to learn. I mean, even just the most simple climate metric of global mean surface temperature, there's still a large uncertainty in end of century projections. A good chunk of that is from the model uncertainty, how well we actually know the system, as well as the rest of it being scenario uncertainty. And a good chunk of the model uncertainty is coming from the ocean, particularly through the heat uptake efficiency and through the carbon processes and through things like the pattern effect and the impact on the atmosphere and SSTs impacting clouds and stuff. So I think there's a large uncertainty. Like, I think there's still first order value in improving ocean simulations for climate.
I guess I just wanted to say the provocative thing that, and I'm not saying this is maybe what should happen, but we have shown that if you wanted to dedicate resources to rewriting your model to run on new architectures, then you would be able to do quarter degree millennial simulations. So it's just something that, you know, probably should be on the table at least.
Well, regardless of whatever our kind of workhorse resolution is, we still need parameterizations. And I think, I mean, we need the higher resolution and the ultrafine to be pushing the envelope in order to help us understand what's going on at these small scales, which we need to parameterize. But I would say that if we're going to give up on coarse resolution, it's giving up on understanding the ocean, because the parameterizations are an encapsulation of what we understand. They should be, at least. And, you know, if we are unable to build coarse resolution models with good parameterizations, it tells us we have failed. We don't understand what's going on. So I would say that that should still be the goal, understanding and, you know, having a theory and explanation of what's going on.
Yeah. So kind of responding also to Paul and so, but no, I mean, just in general, right? Because there's been this like question about like what are the downstream applications, and I think when we talk about regional models, right, there's a real problem if you don't advance the resolution of the climate models and still follow the projections and the protocols. Like, you can't force a regional model of the ocean with a 100-kilometer grid cell, right? Like, you don't get much out of that. So even downscaling the forcing for like the atmosphere, right? So you actually get some of the fine scale structure, which requires a higher resolution ocean and like so on and so forth. You know, there is real value. I think the question, though, I do think where the question is like, is CMIP the goal? Is that where we spend all the resources to improve the CMIP ones and hope that the downstream effects are good? Or do we all start focusing on some of the regional efforts as well and incorporating some of the results from the regional efforts as part of the metric of is CMIP 7 successful, CMIP 8 successful, and going on and so forth.
So Alistair's comment prompted me to think an ideal world in which, consider an ideal world in which we could run, say, a meter resolution, 100 years in a day simulation time using Oceananigans version 10 or something like that. At that point, you wouldn't need to parameterize the eddies for practical reasons. You would probably be wanting to think about parameterizations for curiosity reasons to understand. And I think that a lot, and so that sort of take a little less of that ideal and say, I think what I'm hearing from the Oceananigans people is maybe we could have more of the simulations cheaper and maybe have less of a urgency to parameterize if we put more resources into actually representing explicitly. But the understanding is going to be there. And I agree that they encapsulate our understanding quite nicely, parameterizations do. But it's whether we really have the gun to our head because we have to do it, or it's like we can do it because it's just a curiosity-driven question.
Yeah, there's a very strong emphasis on climate in this group here in the discussion, but there's a lot of discussion about nature run or runs that are run for a few decades at very ultra-fine resolution, so that observationalists for ocean prediction, comparison with the observation that is needed as well. So just a comment.
Also a comment to what Alistair said and Stephen.
It's all right. Yeah.
Yeah. That basically means that we shall not go for all these AI-based parameterizations, right? Or at least restrict to those who could explain something.
You're checking your phone. There was actually a common theme in quite, I think, all of the AI talks, which was they still were trying to understand something. There's a huge benefit in knowing that something is parameterizable. You know, trying to build a theory when it's not actually parameterizable is basically wasting your time. So if a data-driven approach shows you that something can work, then and so we saw this in Akash's talk. I mean, first of all, he built a black box neural net and it worked. So now then figure out what the math is that goes in behind it. So I think that's a common thing. I mean, especially for Lausanne's work, it's all been about trying to understand and derive something beyond what we have now. She wants to understand the physics. So I think, you know, take that literally, because otherwise I agree with you.
I totally agree, but it restricts our methodologies. Sorry, not restricts, but we have to keep that in mind all the time and not just try to cure it by simple AI methods.
I totally agree.
I've got a general question about model tuning and whether there's additional things need to be considered when you're tuning very high resolution ocean models, in particular regional models, and how much, if you've got one region versus another region, but the same model and the same settings, how much overlap there would be, or how much additional model tuning would be regionally specific to get your model in that high resolution region right.
If you're tuning for different regions, it tells you that you don't understand the physics. If you understand why you're tuning for different reasons, maybe you do, right? If something involves F and you're tuning it because F is big in one place and it's zero in another, that's something, but it usually is an indication of a failure of your theory. If we have done a good job, our parameterizations will work all over parameter space or turn themselves off when they don't. And now there are macroscopic tunings that we always tend to do for like climate models. We tune the overall radiative balance of the atmosphere by adjusting some albedos within ranges of plausible uncertainty, just because if the model as a whole drifts, it's useless. And we know that there are aspects of microscale turbulence interactions with cloud aerosols that we don't understand, and that's fine. But for regional applications, a lot of the reasons why we tune is to control drift. The offshore boundary conditions take care of that for you. And so in the regional configurations in particular, if you're having to do something different in different places, it says that is a process worth paying attention to because we don't understand it.
Okay, we've got about 1 minute left. So if you have any overarching comments, that would be great. And I realize that I didn't ask the early career researchers. So if any of you all have a final comment. Okay.
Let's pass it on to.
Yep.
I'm doing this. Okay, so we're now going to move on to. Oh, there's one more question.
Thank you. Yeah, I just wanted to address the bunch of comments that were going around. Also, the question I think was in the previous slide. It was about pushing the resolution, resolving mesoscale, sub-mesoscale. I forgot what the question was, but yeah, the first one with the cost benefits and so on. But what I actually wanted to say here, that besides this, it's important to consider that we need to push the understanding of the small scale processes when we resolve them and how they interact with larger scales and among themselves and how they contribute to, for instance, energy transfers, because just resolving them is not solving the problem. We still need to understand what they're doing and how they're feeding back to the energy cycle of the flow.
Right, and thank you. So should we have just a round of applause for the last session quickly? Okay, so we're now going to move on to perhaps the most important and interesting session. Sorry, no, I am biased. But we have Rainer in the audience today, which is great. So good timing in terms of for this session being at the end here. So we're going to have 5 talks about the vertical and how to do the formulation and coordinates. Our first talk is from Andy Hogg.
Thanks.
20 minutes, I'll give you a 5-minute warning.
Thank you. Okay. So I'm going to talk about some work we've been doing for quite a while now. It originally started with it's not going to work, is it? There we go. It originally started with Angus Gibson, who is a PhD student at ANU. And when Angus finished his PhD, he handed it over to me to finish. And that's why it's taken such an incredibly long time. So I'm going to talk about an adaptive coordinate for the vertical direction, vertical coordinate. And I just want to point out, in case you didn't know how special the vertical direction is in ocean models, the ocean has an aspect ratio like that, right? So it's really weird that we have grid cells that are, maybe 1 meter thick, but hundreds of kilometers wide or at least 20 kilometers wide in an eddy permitting. So obviously we need different techniques for the vertical as we do for the horizontal directions. So I'm going to start with this plot here. This is just a section, a transect across the Southern Ocean in a really idealized bathtub sector model that I run. It's like a re-entrant channel for Drake Passage. Otherwise, it's just a bathtub with sloping sidewalls. And I just want to point out before I tell you anything that most of the plots I show, they're going to have a really distorted depth axis. And that means that you can basically see all the coordinates. And what I'm showing in the white lines there is a pretty standard Z-star formulation with 75 layers. And in the background, I'm showing the temperature or the density. It's a linear equation of state in this model. So we've only got temperature. And you can see that obviously these coordinate surfaces cut through the, what have I done? Cut through the temperature surfaces. And that means if you've got horizontal motion along your coordinate, then you're probably doing spurious mixing. And likewise, if you have any vertical motion at all, you're also doing spurious mixing. So we would expect in a simulation like this, you would have a significant component of horizontal and vertical spurious mixing. And we've heard a bit about spurious mixing. We've also heard a bit about ALE. So now's the part where I have to explain ALE to you with the Jedi Masters sitting right in front of me. And we'll see how I go. If you want to know all the gory details, Steve's paper from 2021 has it all. But I like to simplify things because it makes it easier for me. So I want to imagine that we're we've got a grid cell, okay, and this grid cell is adjacent to the lower boundary, okay, so there's no flux through the lower boundary, and the point is that on this grid cell, we might have some velocities in through the sidewalls. The grid cell has a certain thickness, and you can have velocities at the top of this grid cell, and I'm pressing the wrong button, and you can think of the velocity in the vertical as being either through the interface or a vertical motion of the interface, okay? Now, in an Eulerian model, such as here, the vertical velocity of the interface is essentially zero. So this W grid is zero. And at the end of the time step, W grid is just about what it was. Sorry, at the end of the time step, the thickness H is just about what it was at the start. When you go to an ALE model, which is what we have in MOM6, you do a dynamical time step where your W grid is just the convergence of the flow. And from that, you can calculate how thick the new grid cell is. And then you can say, actually, I'm going to change what that is. And you can actually say whatever you want. You can make H target whatever you want. You've got enough rope to hang yourself. There's lots of bad choices you can make in H target. The question is, what's the optimal choice you can make? And then after you know what your new grid cell thickness is, you can you adjust the WS, the vertical velocity, to make everything balance. Okay, so that's my explanation of ALE for dummies, and this provides us with a lot of flexibility. One coordinate that you've heard a lot about already, and you'll probably hear more about today, is this hybrid sort of HICOM1 case, and this is actually quite simply formulated, but quite powerful, in that what it does is that in regions close to the surface, where isopycnals, as you can see, are pretty much vertical, you end up, you configure it so that you have very close to geopotential coordinates. And that's really what you want in the mixed layer, because even if there is a bit of numerical mixing in the mixed layer, you don't really care because there's so much explicit mixing. But in the deep, you can see this hybrid coordinate switches to something that's truly isopycnal, or very close to isopycnal, and follows isopycnals throughout the ocean, follows the isopycnals as you go through eddies. And so this is a very neat coordinate, and it's a good way to have H target. There's some wrinkles with the HICOM1 coordinate. I'm showing here a case where you have, like, right below the thermocline, some really thick layers that seems to be very difficult to get rid of. There's some other issues with overflows. So HICOM1 coordinate is by no means perfect, but as Steve showed earlier, it's done a lot. So I'm going to propose today to explore an adaptive coordinate which can evolve with time. And we want something that has something like the qualities of this HICOM1 coordinate, in which we're going to have, geopotential-like at the surface and isopycnal-like at depth. But there's going to be a few changes to what you see here in this new coordinate. There's no guarantee this adaptive coordinate is going to be better, but it's sort of been fun trying to see how we can make it. So how are we going to do this? Well, what I've said is that in the deep ocean, where we have stratification, I'm showing the isopycnals here in purple, we would like the coordinate surfaces, which I'm calling ZK, to follow these purple lines fairly closely, okay? So we want the coordinate surfaces to align with isopycnals. And so the way we can do that is by adjusting at each time step the height of the coordinate surface according with the curvature of the density. And what that will do is, over time, it will gradually push the coordinate surfaces towards the density surface, and presumably when the coordinate surface goes up and down, it will follow that. When the coordinate surfaces go up and down, the isopycnal surfaces will go up and down at the same time. And so this is something that we want to operate pretty much whenever it's stratified, okay? So that's the first case we want to cover with this coordinate. The second case we want to cover is near the surface, because we know that near the surface isopycnal isn't going to work, and if nothing else, the reason why it's not going to work is just because these isopycnals are too steep. So in that situation, what we want to do is we want this coordinate to flatten out. And we do that by specifying the evolution of ZK to be just proportional to the Laplacian, so it just smooths out any wrinkles, okay? So we have two cases that we want to follow, and we have a pretty good criteria for when we want to choose one or the other, and that is really the slope of the stratification. So the adaptive grid coordinate, as we call it, solves at each time step, pick whichever time step you want in MOM6, at each time step an equation for the evolution of the coordinate interface. And it does that through a term which is a Laplacian of the density. Sigma is density here, and so we've got something proportional to the Laplacian of density, and we call that the density adaptivity term. And so this is smoothing out the coordinate to follow the density interfaces locally. We have another term here, which we're calling the lateral smoothing term. We sometimes call that the pressure adaptivity term because it actually just takes the pressure or the height and it smooths out the coordinate on that. And we have a term omega, which can be used to switch between them. And so what omega does is when we're in a stratified region, in other words, when the isopycnal slope is smaller than a certain value, we want this term to be preferenced. So we set omega sigma to 1 and we set W omega Z to 0. On the other hand, if the isopycnals are sloping too steeply, we set omega sigma to 0 and we set omega Z to 1, and we preference the lateral smoothing term. And there's some other terms here which I'm just not going to talk about today because they're too annoying and I wish we didn't have them, but anyway. So you can see that if you do this, you're going to get a very sharp transition between your stratified and unstratified regions, and something we've been trying to work with for the last year is the noise basically that gets introduced by that sudden transition. And in the end, after a bunch of trials, we've solved it by just smoothing omega sigma after we calculate it. So we just do a little 5 grid point smoothing, and so we smooth out the transition between stratified and unstratified, and that seems to make things pretty happy. So this is the same section with the AG coordinate, as I showed you before. It's got some interesting features. Some of them you might have expected, some of them you might not have. And I'm just going to take a quick tour through 3 regions. I'm going to look at the surface region. I'm going to look at stratified region, and I'm going to look at the Southern Ocean where we have kind of large-scale structure on the isopycnals. So the surface region, this is all pretty good. This is what we expected. We have almost vertical isopycnals. We have coordinate surfaces which just flatten out through to the lateral smoothing. And we're pretty happy. And every now and then you can see, you know, maybe there's regions where the isopycnals aren't quite steep enough and you get a tiny little bit of slope kicking in, but that's pretty minuscule really. And so we're pretty happy with that component of it. In the eddying regions, this is in the Gulf Stream of my sandbox ocean. And what you can see here is on the eddy scales, the isopycnals are roughly followed by the coordinate surfaces. Now there's exceptions. So sometimes the isopycnals get too steep. Sometimes my pointer won't come back down. Anyway, sometimes there's points where the isopycnals get too steep and the coordinate says, no, forget about it. I'm just going to keep going here. And there's some points where there's a little bit of grid scale noise in the coordinate surface, but generally we're pretty happy with that. The thing that surprised us when we first implemented this is that we thought we were implementing an isopycnal-like coordinate that would follow the isopycnals throughout the ocean. But of course, our coordinate's only locally isopycnal. So when you have eddies at the local scale and a broad scale, you know, upwelling or tilting of the isopycnals, you don't follow them, because this coordinate can only see locally. So we're not getting this coordinate to follow up the interfaces right up to the surface. And at first we were very surprised by this, and then we realized, actually, no, that it's doing exactly what we told it to do. And this actually has the advantage that you don't lose resolution in the vertical in places where it's weakly stratified in the deep. So we've had to think about this and concluded, actually, this is probably what we actually want. So we're sort of happy with that as well. And just to confirm that if you look at the long layer temperature gradients here, of course, near the surface where you have flat coordinates, you've got very large temperature gradients, and they die away once you get into the stratified region. It's not a sudden transition. Some of these persist slightly longer than we'd like, and we're still trying to maybe understand that, but we certainly eliminate most of the long layer temperature gradients. In the last week, we've managed to get this running in a global model. This is like a very early version of Access, what we're going to call Access OM3, which is similar in architecture to the next CSM. And you can see the same thing. You've got geopotential near the surface. You've got coordinate surfaces following eddies, but you don't have any large-scale structure to the coordinate surface, which is consistent. And now, if I can just kick this off. So this is just showing how the coordinate surface behaves in time, and you can see that it's evolving, picking up the eddies, enhancing when they're eddies, and generally doing what we'd expect. And of course, every now and then you get a spot where the isopycnals are so steep that the coordinates just plow through them and say, "Yep, going to forget about that one." Oh, not that one. That way. Okay. And just to show you, the Pacific does something like the Atlantic, and again, sometimes, you might say some of these variations in the isopycnal in the coordinate surface are pretty sharp, but actually mostly they seem to be pretty well resolved. Okay, so I'm going to stop there. The summary is, finally, this coordinate is working. We've managed to put it in the global model. It looks sensible. It looks like it's doing what we asked it to do. It does need more testing, and particularly it needs more quantitative assessment. Jan Ziek is going to help me by implementing his accurate calculation of numerical mixing. And I think we need to look at what sort of climate emerges from this, which I haven't had time to do yet. Thanks.
Okay.
Can you,
Thank you. Thanks, Andy. Your equation for updating the depth of the vertical coordinate partial derivative of z with respect to t, so it had this Laplacian of the horizontal Laplacian of the potential density. And so I'm just trying to understand if you actually have a concavity to the potential density, it'll say that the coordinate should go down, but you'll still remain with that concavity to the potential density, so the coordinate will keep going down. So what, this scheme will stop it with other things when it gets to be too steep, but I think that Laplacian of the potential density shouldn't it be more of like a divergence of the error from neutrality?
So does it answer your question if grad h is a long layer, a long coordinate?
Maybe I'd have to think about it.
Yeah.
But so is that what you're doing?
Yeah. So grad h is the along coordinate gradient.
Okay, I just wanted to ask about your comments at the end. So maybe this is known to many here, but I just wanted to know what you thought the geography of numerical mixing was in terms of spatial and temporal scale, and comment how this approach might help get you at that in your next step, if you don't mind.
Yeah, so I think at a quarter degree, which is what these simulations have been, I reckon most of the numerical mixing is where you have intense boundary currents or where you have eddies that are, partially resolved. And actually, probably the largest numerical mixing is right near the surface, but I'd say we don't care about that. I think it's the numerical mixing beneath or around and beneath the thermocline that we care about the most. And in eddying regions, I think it's going to be largest. So that's where we can look for an improvement.
Okay. So you've been focusing on the sampling of the density, but the big reasoning behind the HiCom1 coordinate is that you want to be either geopotential or density based, so that you do not have any pressure gradient error when you compute the pressure gradient force. As soon as you move away from those two natural coordinates, you're going to have an error in the pressure gradient in your velocities.
I guess, yes, you may. I've talked to Bob about this, and Bob assures me that we can do this. And maybe it helps if you know that the coordinates are still locally isopycnal. So the pressure gradient errors will probably be local.
But it will be there.
Yeah.
So if you go back to the traditional Montgomery potential and gradient of density on surfaces form, or if you're in Z coordinates, there's equivalent, a sigma coordinates, there's equivalent. You have two separate terms that are discretized separately. If those two terms are of the same sign, then the truncation error is guaranteed to be small compared to the total. If they're not, that's where you get real problems where the truncation error becomes large compared to the physical signal. One of the beauties of this is by design, the coordinate surfaces always fall in the wedge between isopycnal and Z, which are the two limits where the extra terms, one of the two terms goes to zero. So reasonably confident that this keeps you in a place where the pressure gradient errors are unlikely to become problematic.
Thanks, Bob.
Steve, ask a question.
So Andy, in one of your last slides, you had a lot of noise in the grid field in the coordinate surfaces. Can you comment on that?
It's not perfect. I haven't investigated them, and it might be we just need to be a bit more careful. This S max parameter, where you set the slope, that really controls how things behave, and so we might need to be a bit more careful and do some more testing on that. So.
Okay, think Andy again. Next up is Matt Bentsen. When it's time to start.
Thank you. Yes, I will present our work on implementing hybrid vertical coordinate in the Bergen layered ocean model. Bergen layered ocean model is the main application is as the ocean component of the Norwegian Earth System model. It is a descendant of Miami isopycnic coordinate ocean model, but further developed. So the AIL method has been quite well introduced, but I have a slide on that. I will talk quite a bit about our challenges with reconstruction, vertical coordinate and regridding. Talk a bit about adapting physical parameterizations to the AIL coordinate, and some results from coupled ocean CI simulations focusing on the impact of the reconstruction accuracy. Yeah, so this has been introduced quite well. I will focus on this high order reconstruction, how we go about that, and the regridding. The fine remapping is kind of straightforward when you have established the new grid and have the high order reconstruction in place. So we use for the reconstruction piecewise polynomial method, and this is heavily inspired by the work by White and Adcroft 2008 and White et al. 2009. We support piecewise constant, piecewise linear, piecewise parabolic, and piecewise quartic methods, reconstructions on non-uniform grids. And for PPM, there are parabolas that is part of the reconstruction, which is defined by the cell mean and edge values. And for the piecewise coordinating methods, we use coordix, which is defined by cell mean, edge values, and edge slopes. As in these works here, we use complex schemes that forms an implicit system, a tridiagonal system of equations, to obtain edge values and slope estimates. I'll not go into much detail here. On the boundaries, we use explicit schemes with selectable order from first to sixth. We'll talk a bit about challenges that we had to obtaining robust reconstructions. One is associated with highly variable cell widths in the stencil. And we come up with a kind of a criterion that we need the cell widths in the stencil to obey. Basically, if there are very thin cell widths in combination with thick, we do merging of grid cells, which is only used for the reconstruction and remapping phase. So this is not impacting the actual layers outside, but it's only an internal correction. Then with high order schemes for obtaining coefficients, the sixth and fifth order schemes, they can quite often lead to rows in the tridiagonal system that are not diagonally dominant. And then you can get these kind of nasty reconstructions easily. So what we do there is that when that occurs, we replace that specific row with reduced order scheme, which is by construction diagonally dominant. So this happened actually quite often with a piecewise coordinating method. This happens in 10% of these high order rows. Then I'll turn to limiting. So the piecewise parabolic method, the original paper by Colella, 84, contain a monotonic limiter that we use. Piecewise coordinating method in White and Adcroft 2008, they developed a monotonic limiter. So those monotonic limiters are the basis of this new non-oscillatory limiting that we are mainly using now. Just to explain very briefly what that is about. I show here a piecewise parabolic reconstruction with no limiting. And we see here a new local extrema formed and some oscillatory behavior here. On the right, that is the result after ppm reconstruction with the standard monotonic limiting. And the orange reconstructions are reconstructions that has on-a-gun limiting. What we do here is that we look at the sign of the second derivative of the reconstruction, which is easily obtained when you have formed the reconstruction. So basically, if we have 3 consecutive cells with the same sign, we don't apply limiting. So here we don't apply limiting, and not here. So I'll show some results on that later, not much detail. The reconstruction is also very sensitive to limiting at the boundaries. And the only kind of strictly monotonic approach possible is piecewise constant. But that leads to, in a hybrid coordinate, to the formation of very deep layers close to the bathymetry. So our preferred option is a kind of Neumann boundary condition, where the derivative of the reconstruction vanishes at the boundary, and then some constraints on the slope of the edge next to the boundary. Here is just showing all the kind of reconstructions, all the limiters available. This is a test case doing 1,000 remappings between a uniform and a randomly perturbed non-uniform grid. So we have piecewise constant, piecewise linear method, piecewise parabolic, piecewise quartic here. This is showing at the left unlimited, monotonic, non-oscillatory, and non-oscillatory, which can be easily extended with a positive definite option. So what we see that, we increase accuracy with increased order as expected. We see the monotonic limiter is severely pressing these marginally resolved features. The non-oscillatory limiter, these are much better maintained. So this is our preferred method. But there are also other advantages than accuracy, I think. Just the digression, this also works for 2D advection. So this is just showing that in a deformation flow test, using this quite simple non-oscillatory fix really improves maintenance of a smooth extrema. Okay, then I'll turn to vertical coordinate and regridding strategy. So currently in Blom, we have implemented P level, so that's equivalent to set level in Boussinesq model, and hybrid. I don't go much in detail about the hybrid coordinate because it's very similar to HICOM 1, I think, in MOM 6. And of course, this is really relying on the approach from that was started with HICOM. The hybrid coordinate, that is hybrid between continuous isopycnal, that is prescribed sigma 2 at layer interfaces, and pressure levels. Regridding of the continuous isopycnals, that was quite challenging. We explored first the regridding by direct intersection with a reconstructed density profile. And to the right, you see some ways to do that. You can use the direct reconstruction, or you can use some kind of a more continuous profile. But what we have ended up using is that we, instead of doing a direct intersection, we nudge the interfaces to gradually reduce the deviation from the prescribed density at the interface. I will also mention that we found a transition zone very beneficial between the continuous isopycnal and the pressure levels to smooth the change in the vertical resolution. I think we saw some examples. There's also a very abrupt change from the geopotential or pressure levels to isopycnal interior. So just a bit about the impact or the sensitivity to the regridding approach. This is showing what we get in a long simulation using direct intersection. A lot of trial and error. We never got it really to work. We get this unsatisfactory layer structure developing. This is exactly the same using the nudging approach. So we get a much more robust and pleasant layer structure. Then about this transition zone. So this is a bit what we saw earlier. Then if you don't do anything in the transition, you get very sharp transition between continuous isopycnals and pressure levels. And you get a large jump in vertical resolution here. So what we do here is that we introduce a transition zone. We find basically where this is happening in the column. That's this dot here. Here the green dots are density at pressure level interfaces. And the blue dots are the reference densities that you're seeking. And then in a transition zone, we kind of smoothen out these target densities that we're trying to achieve. And by doing that, we can have this kind of solution instead of this very sharp transition. Also, the choice of limiter has a strong there's a strong sensitivity to the choice of limiter. When we use the monotonic PPM, we get formation of unrealistic layer structure, while non-oscillatory limiter gives better results in our experience. Physical parameterizations with Ale method. I don't have time to go in much detail at all. We use KPP as implemented in CVMix. We have made some changes. We use a non-local distribution of surface momentum flux, and also we have a non-local distribution of brine from sea ice freezing, which was important to reduce the deep mixture bias in the Arctic. We are missing enough mixing in gravity currents with KPP, and we are struggling to find a way to handle that satisfactorily, which is also a proof that the hybrid coordinate is preserving water masses quite well. We have implemented neutral diffusion along non-local neutral sublayers for eddy-induced diffusion, as recently proposed by Shao et al. 2020. Yeah, I don't think I have time to talk much about that, or to say that it's complicated to implement. It's quite expensive computationally, but it's super flexible. It works in any coordinates that you choose. And eddy-induced transport, we have GM implemented more or less as before, because we made that kind of vertical coordinate independent. Now we can finally also implement fully submesoscale eddy-induced transport with resolution in the planetary boundary layer. Then we'll show some results from coupled ocean CI simulations that is run in the NORSEM framework with size 5 as the CS component. We use here OMDP forcing. It's a tripolar grid with 1 degree resolution along the equator. 56 vertical levels. We're trying to match the resolution we have been using traditionally with isopycnic coordinates for comparison. We are exploring a higher vertical or more vertical levels, but what I will show here is 56 vertical levels. Minimum thickness of the top layer is 2.5 meters. I will mostly be showing figures from as a mean of the last 20 years of the second cycle of the GRA cycle. So here are our 3 currently supported coordinates. We have the old isopycnic, hybrid, pressure level. This showing temperature in a Pacific section. And we can see that within AL coordinates, we are finally getting rid of something I've been struggling with our isopycnic formulation, with too much deep convection in the Southern Ocean. I'm not sure if there's something intrinsic or we're just lucky here, but anyway, that's a big improvement. But overall, there are many things that are very similar in the isopycnic domain. And I was also very surprised to see the similarity of pressure level and isopycnic in representing upper ocean features. What I'm showing here is zonal mean temperature difference compared to observations. And I have 3 realizations of pressure levels in the top, and at the bottom, I'm using the hybrid coordinate. The difference here is that to the left, I'm using piecewise linear method, in the middle, piecewise parabolic method, and to the right, piecewise coordinate method. So increasing at least expected accuracy towards the right. I think that generally you can see that the pressure level, there's more of a warm bias in the upper ocean. And we can maybe also here see that with the lowest accuracy method, there is more bias. All the hybrid are fairly similar. If you zoom in on the difference, we can see that ppm versus PQM, there's very little difference. While when we compare PLM with PQM, we do see differences appear. And if you look at the global mean potential temperature evolution, we see that the pressure level coordinate has a stronger temperature drift, while with hybrid, there's less drift, and they're all very similar. Looking at AMOC, we see that pressure level has generally a weaker AMOC strength. With hybrid, it is a bit stronger. It also has a deeper reach, which is also nice to see, expected in a way, but not obvious. And here is the time series of AMOC showing that a lot of similar variability, but that hybrid stays stronger. Yeah, so I just end with this summary slide.
We have 3 minutes. Dimitri.
Thank you for your presentation. I'm Dimitri from PSL. So you use 56 vertical levels, right? Were they packed mostly at the top layer or in the deeper layer? The reason I'm asking this question is I had a lot of troubles when I tried to implement high resolution vertical grid with HiCom, because in the deeper ocean, where the ocean close to be homogeneous, the difference between target densities is very tiny. It's like 1 to the 10 to the minus third order, right? So, and it causes a lot of problems during the simulation. Did you have anything like this? Can you comment on this?
Yeah, I mean, so basically we're using the same kind of density class as we used previously with isopycnic coordinate and used in SIMU5, SIMU6 simulations. The vertical resolution there is really marginal, and it's not really adequate to represent, for example, solar and ocean. But we chose that now just to have a clean comparison. It is a kind of I think it is a decent density classes for a global application, but looking at the regional or specific regions, they're not optimal. So that's of course a challenge with the density coordinate. How do you pick density classes that are a good compromise globally?
Are there any other questions? Can I ask a question? I mean, I'm not meant to, but you showed that there wasn't much gain between ppm and pqm, but that wasn't in, this was with physics in your solutions, right? So do you think it's just that the errors that we've got at ppm are just smaller than the physics now? I mean, if you did the same tests with an adiabatic model, I think we would always.
Yeah, and I think we should also have some other metric to look at this. And I was thinking, I mean, when I go home, I will look at the potential energy change when doing this construction remapping. Of course, this is not an eddy resolving model. It would be interesting to see what is the impact of higher order methods when you have more variability. So this is 1 degree.
Okay. Last question.
Does the non-oscillatory limiter cause any additional cost to the model performance?
That is very modest because we already do the reconstruction and just checking the sign. That's basically there. So I would say that's quite modest.
Thanks.
Okay, so let's thank all the speakers for the first half. Okay, everyone. Who's the note taker for? Thank you, Kate. Right. Okay, seats, please. So, thank you for getting here back on time. We're going to continue the vertical coordinate. What is the title of the session? It's called Generalized Vertical Coordinates and Formulation. And this talk will be online from Alan Wallcraft, who, thanks for joining, Alan. I know you've just had COVID, so I'm glad you can make it. Take it away. And you're muted right now. Alan, we can't hear you.
So the basic regridding.
Start from the beginning, because we've only just got the microphone turned on.
Okay.
Thank you.
So the basic Ale approach is for each time step, solve the layered continuity equation. So you move the layers and then apply Ale in the vertical. And the regrid step selects the desired layer structure. And both HICOM HibGen and MOM6 HICOM 1 favor isopycnals that outcrop into fixed depth layers. And once you have the regridded layers, then you remap from the source to the regrid layers. Interfaces move, but the fluid does not move. And choose interpolation that's conservative. And typically that's ppm with layer edge values from a cubic polynomial. This normally doesn't change the solution, but it does add diffusion. So in HibGen, regridding uses entrainment. So source and both the source and target is layer average sigma 2 potential density. And the approach is to maintain isopycnal layers. So if a layer is too heavy, entrain from the lighter layer above, and if a layer is too light, entrain from a heavier layer below. And sometimes an interface needs to go up and down. So we can only pick one. And for this, and for other reasons, we can often get thick layer structure. The major trick that HibGen uses is it uses PCM for near isopycnal layers for both regridding and remapping. Now, This greatly simplifies entrainment and detrainment regridding. For example, detrainment does not change layer density at all. However, PCM is first order accurate and very diffusive. But the point here is that regridding does not affect most isospectral layers. If you don't do any regridding, then there is no loss of accuracy or diffusion. To fix the non-isospectral layers, we typically use PPM with a Wiener-like cubic polynomial for the edge calculations. It produces noisy interfaces, and so you actually require an additional interface smoother with its approach. So in contrast, in MOM, we have HiCom1, and this regridding here walks a monotonic vertical profile. So the source is layer sigma 2 potential density, typically with a 1% compressibility added. So this is usually monotonically increasing, and if it isn't, then it's forced to be stable. And from these layer densities and the layer thicknesses, construct a vertical profile using piecewise polynomials. Now, regridding and remapping can use different profiles, and the only practical scheme in the original version in MOM6 was P1M H2, which is linear between H2 interfaces, which is not a remapping scheme, but it's used for the regridding. But now we have PPM CW, which adds a monotonic profile constraint to the typical H4 edges, and that's now the recommended option. Now, the main difference with Hydrogen is that the target is interface sigma 2 potential density, as opposed to layer potential density. And the new interface depths are at the location of the target on the profile. And if we have a monotonic profile, then there is only one valid place where that happens. So we have a unique mapping. And for remapping, after the regridding, we typically use PPM H4. However, now we have PPM CW, which is slightly more diffusive than the H4 version, but it can be used for both regridding and remapping. And this typically produces smooth interfaces, no need for an additional interface smoother. So I'm going to be talking about several test domains, and they're all based on the NABIS GOS 3.1 forecast system. And this uses a 41-layer, 12-degree global tripole grid HiCom setup. And so what I have is twin MOM6 and HiCom simulations on this domain. And the plot is a vertical cross-section, top 1,000 meters in the middle of the Pacific. And the thin black lines are the interface locations. And what you can see is near the surface, we have some fixed depth interfaces, fewer of them near the equator. And at very high latitudes, in fact, these fixed depth layers can extend below 1,000 meters. If you look about 3/4 of the way to the right across the HiCom plot, you can see thick, thin, thick, thin, thick layers. And this is a 3-year mean. So these layers are thin all the time. So they've essentially disappeared. And we've actually lost some resolution in the vertical. In the interior of these sections, you can see that the layers are approximately isopycnal. And even though the two are using a different regridding scheme, they're looking, remarkably similar. So how do they differ? Hydrogen assumes the source layer structure is close to the desired result. That's why the entrainment and detrainment can work. HiCom1 makes no such assumption. In fact, it's a general vertical interpolator. And perhaps because HiCom1 exists, MOM6 requires a vertical interpolator. And Hydrogen can't fill this role. I pointed out that Hydrogen often produces thick, thin, thick layer structure, and HiCom doesn't do that. The major difference, though, is that Hydrogen maintains isopycnal layers exactly, but HiCom1 does not. So if a layer changes thickness adiabatically, its layer potential density is unchanged, and that's what's used in HibGen. But its interface potential density is not unchanged because this depends on nearby layer thicknesses and densities and the compressibility factor. So the associated interfaces are moved by HiCom1 and preserved by the HibGen regrider. So in general, HibGen moves interfaces significantly less than HiCom1. And that implies that HibGen causes less dipycnal diffusion than HiCom1. So this is the overturning stream function from those twin experiments. And on the left, you see that the HiCom AMOC is perhaps a little weak, but it's realistically deep. I mean, at the rapid array at 26 north, the zero Schroeder crossing line, which is the thick black line on these plots, is at 4,300 meters. And in HiCom, it's at 3,500 meters, but then it immediately deepens to 4,000 meters south of 26. On the other hand, the MOM6 AMOC is 1,500 meters too shallow. And in general, an isopignal favoring model should have a deeper overturning circulation than this. So it's hard to do tuning on a 12th degree global model. And so what I've done here is configure just the Atlantic piece. So you cut the Atlantic out of the global model. The Atlantic is still pretty big, but it's a lot smaller than the globe. And so if we run the original HiCom1 case on this Atlantic domain, we get a similar AMOC as before, although it's slightly better because now we're constraining the north and south boundaries to be correct, to be at climatology. But now on the right here, this is the latest setup with HiCom1. And now we have the zero crossing at 4,000 meters. This is a much more satisfying AMOC plot. So we solved our AMOC issues with the Atlantic domain. The problem is that in the global domain, we don't see as large an improvement. And this seems to be because in the Atlantic domain, the Denmark's rate overflow was constrained to be about correct. And in the global case, it's missing, essentially. And if you're actually running MOM, these are the setup we're using, and the ones in orange are the ones that likely gave us the improvements. Looking in more detail about HiCom1 regridding, the original approach was P1MH2, a regrid with P1MH4 for remap. So why don't we use P1MH4 for both? The issue is that that approach eventually produces unstable layers. Now recall that the new interface depths are at the location of targets on the profile, and in the subsequent plots, that's the cyan curves. But however, the actual new interface densities are remap TNS, not density, to new layers, and then reapply the H2 or H4 polynomials to get the new layer densities and to the new layer densities and thicknesses to get the new interface densities. And these can be approximated by holding the density profile fixed, except for one single interface, and applying the remapping and HCAP recalculation to get the new density at that interface. And that's the orange curves on the upcoming plots. So this is a profile from a single location in the Gulf of Mexico below 1,000 meters. And the black curve is PCM, which is what we would use for HibGen on this profile. But the reason it's on this plot is because the horizontal black lines tell you where the interface locations are, and the vertical black lines tell you what the layer average potential density is. And in these examples, I'm not using any compressibility. Now, the orange squares are the interface densities calculated from the H2 polynomial. And the straight lines connecting them, the blue curve, is P1M H2. So if one of these interfaces is at the wrong density, then we would move that interface up or down the blue curve until we found its target density. But if we do that, we don't get the blue curve, we get the orange curve. And the orange curve is well behaved, it's monotonic, for example, but it isn't particularly close to the blue curve. If instead we use ppm H4 for both regridding and remapping, now the black squares are the H2 interface densities from the previous plot, and the orange squares are now the H4 interface densities. And notice that there's 2 orange squares on many of these interfaces. Generally speaking, if you have a piecewise polynomial remapping scheme, it will sometimes have a density jump at an interface, at one or more interfaces. Now the blue curve is no longer a straight line, no longer straight lines, but it's well behaved. The orange curve, on the other hand, is no longer monotonically increasing. And if you look at the lowest layer here, you see a very strange profile, a zigzag profile for the orange curve. What's happening here is as that interface above deepens, the H4 calculation initially still thinks there should be a density jump on that interface. But when it gets deep enough, it decides that it only needs one density on that interface. And so you flip to a different solution. And it's probably this kind of behavior which causes this approach to be unstable in practice. So we now have this ppm CW as an alternative. And what you see here, that now the black squares are the H4 from the previous slide. And you can see the orange squares you can still have a density jump like on the lowest interface shown here. But generally there are fewer of them. And the orange curve is now very well behaved and is really quite close to the blue curve, except on one of the interfaces in this example. So my third domain example is cut the Gulf of Mexico only out of the global or the Atlantic model. And in this case, we're going to start from Goths on January 1st, 94, and we're going to apply Goths on the boundary. And we run it for 2 months and then extend for 3 days, sampling every time step. And what I'm plotting here is change in layer 34 thickness just from regrid. And what you see here is it's very clear that the ALE is a single column process. There isn't a huge amount of correlation between one grid point and the next grid point, although there is some. The other thing to note here, though, is these plots are one grid point, one time step apart, and they have almost exactly the same pattern, but of opposite sign. So what's happening here is the regrid is moving interfaces, and then the very next time step, regridding is moving them back again. So this is regrid jitter, and it leads to excessive dipycnal diffusion. So we know that, in fact, the actual interface density can be different from the target. So I added the option HiCom1 only improves, which says skip any move that causes a worse fit. And the plot on the left here looks like the previous slide, but now what we're plotting is changing interface 34 density fit from regrid. And positive values, that is the red values, are worse fit. And what you see on the left, which is the original case, and you can see that about half the values are worse. They're red. Now, if we run this thing for 2 months again and then look at what happens with improves equals true, well, first of all, there are no red values, which demonstrates that our HiCom only improves is working. But also, there are actually far fewer grid points that are being regridded at all. So this significantly reduces jitter and presumably dipycnal diffusion. The canonical plot for a Gulf of Mexico model is multi-year sea surface height variability. And on the right here, you see the kind of plot that you would expect to see, which is that loop current eddies periodically shed and migrate westwards across the Gulf. on the left, you see P1MH2, even though also with HICOM only improves. And in this case, what happens is it is form on the loop current, but they don't shed. And this was, and the reason I was looking at Gulf of Mexico is because this was happening in the global and Atlantic cases also. And so we've solved it for the Gulf of Mexico domain with PPM-CW, but it is still shut down in Atlantic and global cases with this setup. So I'm switching back to the Atlantic test case, and essentially what we're doing here is spin it up and then run for 31 days with new AIL options. And we're looking at layer 22 thickness change. And on the left is MOM6 HIBGEN. I noted earlier that HIBGEN is now available in MOM6. The interesting thing about this plot is there's a lot of regridding happening where the layer is intersecting the shelf slope. This is more regridding than I expected to see, so it's a little bit of a surprise. But in the interior, there's essentially no regridding going on. If we look at PPM-CW with only improves, there's some regridding happening on the shelf slope, but there's quite a bit of regridding happening in the interior.
And 5 minutes.
That's great. So one of the properties of an isopycnal favoring model, particularly in a global domain, is that the target density of deep layers is often denser than the bottom density. And this leads to zero thickness layers at the bottom. MOM6 introduced the option max layer thickness, which sets a maximum thickness for each layer. And the effect of this is to split thick isopycnal layers into several layers. So and this leads to more deep inflated layers, but of course at the cost of disfavoring isopycnals. And although this looks like a local option, right, it's layer by layer, the fact is that once one layer is split, all deeper layers will be away from their target densities and so will also be split. So this is a good idea, and I added it to HICOM as DX0K. And in our 41 layer global HICOM setup, when we set DX0K to 750 meters for all layers, it's active somewhere on the globe in layers 24 to 41, and all 41 layers inflate in the Southern Ocean. One of the issues with HICOM is that it uses sigma 2 potential density for pressure gradient with a thermobaricity correction, and this can be unstable. Now MOM6 uses much more modern numerics than HICOM, and it can't have this thermobaric instability. The plots are the difference in sea surface height over 12 hours in the North Pacific, and you can clearly see the impact of TBI on the sea surface height in HIBGEN. So suppose we start from that spun up HICOM case and run for 1 month with DX0K equals 750 meters. And the plot is salinity sections at 170 west and 45 north through that section I just showed you, through that domain I just showed you. And on the left is the initial state. And you can see that the interfaces have lots of wiggles on them. That's the TBI. And also that layer 36 is very thick. Now, when we run for 1 month with DX0K 750, we get the sections on the right, where the wiggles have largely disappeared from the interfaces. And layers 36 to 37 now become layers 36 to 40. And this is a rather strange coordinate, because these interfaces are tracking the interface below the first layer above them that is thinner than 750 meters. And in these sections, that is either layer 35 or layer 34, depending on where you are. The other point to make here is that you can also get rid of TBI just by adding more deep isopycnal layers at the cost of a more expensive model. So in summary, HICOM 1 with PPM-CW and HICOM only improves is a big improvement, but still has more dipeptidyl diffusion than we would like. Further improvements are possible. For example, we can look at alternatives to the compressibility factor. Hibgen, on the other hand, has minimal dipeptidyl diffusion, but it has other issues. The thick layer structure reduces effective resolution, and it requires an additional interface smoothing. The other thing to note is that algorithms and source code are migrating between HICOM and MOM. Hibgen is available in MOM 6, and it exposed a major bug in Hibgen, now fixed in HICOM. And we've added max layer thickness to Hibgen, and there's even now a HICOM 1-like regritter test undergoing testing in HICOM. So that's it.
Thank you very much. I'll let us run over a bit, so I'll have one question. Are you going to be that? Okay.
Thanks, Alan. When you mentioned that with maximum layer thickness, all the layers, if that gets triggered, all the layers below then become non-isopycnal. Have you seen if this behavior, like if it happens in a time step, can it go back to being isopycnal later on in the simulation once it happens?
I kind of doubt it. I think that might happen if it was marginally happening, if the layer was, say, 800 meters thick. But if the layer, should be 1,000 or 2,000 meters thick, then it's not going to happen. And the big issue is this cascade, right? In other words, as soon as one layer is switched, then all the others are now, pushed to the wrong densities, essentially.
Okay, thank you again, Alan. Okay, so next up we have Gabriel Derrida from INRIA. Take it away.
Okay, so good afternoon. My name is Gabriel. So I'm a PhD student under the supervision of Laurent Debreu, Florian Lemarié, and Jérôme Chanu. And so I'm going to talk about basically vertical representation of baroclinic mode, eigenmode. Okay. So yes. Yes, the ocean is an inhomogeneous environment with significant variations of salinity and temperature. Okay. And so to measure this inhomogeneity, one can calculate the Boone bisalar frequency, which is proportional to the gradient, vertical gradient of temperature and salinity. So here I represent a vertical section. Yes, no, okay. Okay, so this is a vertical section of the Pacific Ocean, and you can see clearly the inhomogeneity of the profile. So yes, now the question is now how can we have a discrete representation of internal waves, and this includes the representation of okay. And so this includes the representation of baroclinic mode. Okay, so this question has been discussed in this paper, so please refer to it. Okay, so to answer the question, we use the eigenvalue formalism. So basically, this formalism is about to reduce a 2D linearized primitive equation to a 1D eigenvalue problem. Okay. So assuming Boussinesq approximation and hydrostatic hypothesis, one can write this set of 4 linear equations, okay, with 4 variables, so U and W, the horizontal and vertical velocity, P the pressure, and B the buoyancy, and you can see n square here, okay? And so thanks to a separation of variables, you can have finally this 1D eigenvalue problem. So just to be clear, you can do this only because n squared depends only on z, okay? And so yes, you have this 1D eigenvalue problem, so also called the Sturm-Liouville problem. And so 3 points could be noted. So here, here we have a set of linear equations, okay? So you can write solution as sum of eigenmodes, which are solution of the eigenvalue problem. Eigenvalues are related to the horizontal velocity of modes. And if you want to change boundary condition to add some other terms in this set of equations, it will not give major changes and major modification to what I'm going to say. Okay. So yes, this is an example of vertical mode, baroclinic mode. So for a given Bruns-Weishaler frequency, you have modes which are solution of the eigenvalue problem. Okay, so I represent this here some modes, and after that we can calculate finally the solutions of the 2D linearized primitive equation thanks to a vertical mode decomposition. So here I take the example of n squared equal to a constant because actually you can do analytical solutions. So this is what I'm presenting right here, okay? So I choose to represent the buoyancy. So here the top plot is the initial condition. So it's a localized wave packet and it designs to move only on the right, okay? And so after some times, we see that modes separate to each other because of their different horizontal velocity propagation. Okay. So now the problematic of my talk. So one needs to discretize these 2D linearized primitive equations, okay? And so this gives us a discrete eigenvalue problem. And so the question now is how can we reduce this eigenvalue error due to discretization? So I'm going to present two ideas, okay, to answer this question. So first, I'm going to talk about the staggered grid. Yeah. Oh, sorry. Yeah. Yes, okay. Staggered grid, and after that, I'm going to talk about the optimal choice of vertical level position. So yes, the staggered grid. So historically, two vertical staggered grids have been considered. So the Lorentz grid and the Charney-Phillips grid. So the main difference between these two grids is the position of the buoyancy. So you can see for the Lorentz grid, buoyancy is at the center of the cell, whereas for the Charney-Phillips grid is at the interface, okay? And so each grid gives us a new discrete Sturm-Liouville problem, okay? Yes. Oh, yes, a new Sturm-Liouville problem. And so if you write the eigenvalue as a sum, so you make a perturbation theory, so you calculate the eigenvalue as the eigenvalue of the continuous problem plus a small error, okay, times the vertical resolution you choose, you will have different error due to discretization. Depends on the vertical grid you choose, okay? And so the idea here is to introduce a beta parameter just here, okay, to like kind of interpolate between these two kind of vertical grid, okay? So you see that when beta equal to 0, yes, when beta equal to 0, you have the case of the Charney-Phillips grid, and when beta equal to 1, you have the case of the Lorentz grid. And so now you have a new Sturm-Liouville problem will depend on beta. And so one can ask which value of beta will make vanish the eigenvalue error, okay? Because now the eigenvalue error, the error due to discretization depends on this parameter beta. Yeah, so this is a first plot I want to show to you. So yes, actually there is a value of beta. We will make vanish this error, beta equal 1/3. So this is for a constant Bruns-Weishaler frequency, but we can make similar ideas with when n squared is not a constant, okay? And so here I represent eigenvalues of the Sturm-Liouville problem. So in big dots, you have eigenvalue of the continuous problem, and in small dots, you have some eigenvalues of some discrete problem, depends on the beta parameter you choose, okay? So for instance, in red, you have the case of the Lorentz grid, and in green, you have the optimal choice of beta, okay? So, okay, by interpolating between these two vertical grids, we can reduce the error, at least for first eigenmode, okay? Okay. So, the second idea I want to talk about is the optimal choice of vertical level position. So this is more about the topic of a generalized vertical coordinate. So yes, here I represent two grids, so a regular grid here and an irregular grid, okay? And so the function we want to optimize is h of z, which is the layer thickness of the grid. We can also see that of a local change of scale of the grid, okay? And so if you write as before the eigenvalue as the eigenvalue of the continuous problem plus a small error, okay? This error will depend on now the layer thickness. And so the goal is to find the optimal H, okay, the optimal layer thickness, which minimizes the error on the eigenvalue. So yes, this slide is just to show you that actually we can calculate with some perturbation theory the value of mu, okay? And so we need to add the constraint that actually the total length remains constant, but we have access to like a cost function, okay? Will depend on h squared and something like that. And so one can ask, so okay, so one can try to see if he can calculate an optimal h of z, okay? So he had to make a functional derivative of this cost function and see if h of z equals to. So for one eigenvalue, so okay, this is an example, okay? So I choose a discretization and I calculate mu, but we can choose another discretization with the beta parameter I presented earlier, okay? So for one eigenvalue, in some cases, so with some discretization, it's possible to calculate actually h of z. We can have an analytical approach of h of z, but for one eigenvalue. If you want to see for more than one eigenvalue, it becomes a complicated optimization problem, and so we need to solve this numerically. So yes, this is just a slide to give you the method we use. So actually, the input parameter is the grid, or the layer thickness of the grid, and the cost function is just the sum of relative errors, okay? So yes, here n is the number of eigenvalues you want to optimize. Yes, it maybe will depend on the horizontal resolution you choose. After that, lambda c is a high resolution eigenvalues, because here n squared is not a constant, so we do not have access to analytical solutions. And we also put a weight because we want to give more weight to first eigenvalues, okay, for energetic consideration. Okay, so this is the first result. So I try here to represent mode 4 with 30 grid points. So here is a typical vertical profile, okay? And so here is a regular grid in red, the high resolution grid, and the optimal grid. So what you can see, the regular grid has many difficulties to capture the oscillating part of the mode, whereas the optimal grid can do a pretty good job. Okay, so I'm totally okay. So it's a very simple case, but actually the optimization problem works. Yes. So just I want to mention that yes, I optimize for the fourth mode. Okay. So yes. And if you go back to the propagation test case, so we can, as before, initialize as a localized wave packet, okay, which is allowing to move only on the right. And so you have the case of the high resolution grid here, the regular grid and the optimal grid. So actually all grid gives a pretty good representation of the first mode, okay? Okay, the velocity of the first mode. It becomes, yes, they can represent, we can have a great representation with each grid of the first eigenvalue, but if you see for more higher eigenvalue, the result change. Okay? Okay. I think the time. So just conclusion and future work. So I want to remind that the objective is to improve the representation of internal waves, focusing on the vertical grid, first to see how the staggered of the grid, and secondly, see the vertical level placement, okay? So yes, we saw that it's possible to have kind of an hybrid between the Charney-Phillips grid and the Lorentz grid, which provide a more accurate representation of first eigenvalues, okay? And the question now is, it is feasible in the fully primitive equation model. Okay. And what does it involve? Okay. And the second point is about the optimal placement of vertical levels to represent a vertical mode. So this could be a basis to a definition of a target grid in an highly coordinate. So, but we need also to provide constraint to refining a boundary layer, boundary layer, and also investigate ways to get a cheap estimate to this optimization problem. Yes, and some future work. So I'm going to see with climatological data to compare with conventional stretching functions, used in the sigma and z star coordinates. And also give with zero, we try to have some semi-realistic simulation with the NEMO model. Okay, thanks very much.
Questions for Gabriel? Oh, lots. Two, yep. Choose.
Thanks for the talk. This rings a lot of bells for B and Gustavo, and because we tried something very similar to this with Scott Bachman in MOM6, and we ran into kind of two problems. One was the refinement, like how do you overlay kind of like this optimal grid with something that resolves the boundary layer? But more critically, we ran into problems when we ran it in quarter degree MOM6, where we started getting spurious motion, which I think at the time we were trying to attribute to whether there was a pressure gradient error, because you're not guaranteed to be Z star like, you're not guaranteed to be isopycnal. They can kind of be placed wherever. So we got really weird gradients, like really noisy interfaces and stuff like that. So not to, and we didn't have that much time. It was like I was here for like a week, and we were like, let's try something, and we couldn't get it to work. I'm really hopeful that you find a way to do this, because it's a very, very interesting problem, especially for idealized modeling. So really, really curious.
Ashley.
Great talk, thank you. I was wondering, when applying this to a realistic or semi-realistic model, how important would it be for there to be seasonal variability in the target coordinates? For example, if your buoyancy is changing and your eigenvalues for the Sturm-Liouville problem would then also change, like seasonally, I guess.
Yeah.
Or you don't think it would be very important?
No, okay, I don't really get the question, but the question is, if n squared depends on time also, how does it?
Yeah, so I guess if you pick your target coordinates in one season, but if it's an area where, say, your stratification is changing a bit, then your solutions for the Sturm-Liouville decomposition would change. And then would that change the optimal
yes, of course.
target points?
Yes, of course, it will change the optimal choice. It's why I talk about yes, target grid, because actually the model can okay, so we can actualize the grid. So
so it's being updated.
Update the grid, sorry.
Okay.
yeah, but
any others? There's time for one more. I mean, I was actually wondering not just time, but latitude, right? I mean, there's large variations, and then geographically. So if you're choosing a Z grid, for example, you've got to blend all of those optimal positions, which are going to vary with geography. So
yeah, but it's a problem that the coordinate move a lot with geography. I don't know, but for instance, in the isopignal coordinate, the coordinate change a lot. No, it depends on the latitude you choose. No.
Yeah, that's the point.
Yeah. And your question is, how can we improve it?
I guess I'm asking, you might find that there's at one particular latitude and stratification, you'll find an optimal distribution for up to 5 or 6 modes or something. But then if you go to a whole new latitude and different stratification, the best positions would be different. So the choice is, how do you decide how to blend them together? How do you optimize globally?
Okay. Yeah. I don't know.
Yeah,
Yeah,
it's a work in progress. Exactly.
That question was at least looked at in the Stewart paper, Stewart et al., and you might find some inspiration from what was done there.
Okay.
Okay, thank you very much, Gabriel. And next up is Diego. In fact, Diego, you're closing the show.
Thank you.
My name is Diego, and I am a member of the ocean modeling team in the Met Office in the UK. And yes, today we'd like to present to you some work we have been doing recently to try to combine two-way nesting techniques with the localized multi-envelope vertical coordinates to improve flow topography interactions in our ocean models. So this is, first of all, a collaborative work, and it's not working, okay. Yes, my co-authors are there, and I would like to thank them. Okay, so let's start with the motivation, the background of the work. So what are the issues with flow topography interactions in our models? So first of all, as we know from the nice talk of Eric, for example, this morning, the lateral resolution. We know that increasing the horizontal resolution can be quite beneficial, but in the reality, finite computational resources can limit how much we can uniformly increase the horizontal resolution of our models. And this is especially true in the case of global coupled systems. Another issue of our models is the type of vertical coordinate system, because it dictates the way the model will represent the bottom topography. So for example, in the case of quasi-Eulerian vertical coordinates, we know that rainfall wind levels are better suited to represent flow topography interactions than Z coordinates, even when the partial steps parameterization is employed. However, the vast majority of the ocean general circulation models participating in the last CMIP6 deck actually use geopotential vertical coordinates. And one of the main reasons for this was that classical terrain following coordinates introduce an errors in the computation of the pressure gradient force, therefore making their use in configuration used for climate studies quite challenging. So yeah, our idea is, okay, why don't we use two-way horizontal and vertical nesting methods to locally improve the solution of our quartz parent model? From this approach, we can have several benefits. For example, we will be able to implement a different space and time refinement and physics in different areas of the domain. And so having a high lateral vertical resolution only where we want and where it is needed. And therefore, practically implementing the multi-scale capability for structured models. Also, having zooms with different types of vertical coordinate system with respect to the parent model can allow one to target the main local physical processes at stakes. We will also have no overhead from very large outputs, and the coupling strategies in the case of coupled systems can remain largely the same. So we use NEMO. So what are the nesting capability available with NEMO? So NEMO is online versatile block refinement capability based on the Griffies software, which provides NEMO with conservative interpolation and restriction operators for two-way horizontal nesting. Then lately, Jérôme Chenou et al. 2023 introduced in NEMO a Griff generic vertical conservative remapping operators for vertical nesting. Therefore, which are very similar to the one used from OMDP6 arbitral Lagrangian Aileron framework. Yes, but vertical remapping schemes require exact volume matching within the exchanging zone. So because of length mismatching at the boundaries, this condition could be hard to satisfy when changing the type of vertical coordinate system in realistic applications. So what we propose here is to use the localization method, which is a methodology a general methodology that we recently proposed to embed distinct types of vertical coordinate system in local time invariant targeted areas of quasi-Eulerian ocean models. To briefly give you the idea, let's consider the cartoon on the left-hand side. So this is a sketch of the localization method for the case of two localization area. In the white global area omega, the model will be discretized with global omega v quasi-Eulerian general vertical coordinate system. In the two red area, the model will use localized lambda PV quasi-Eulerian general vertical coordinate system, and in the two green area TP, the two vertical coordinate system will blend one into each other. So very simple. Then we use this method to localize multi-envelope as coordinates to implement quasi-terrain following levels in the Greenland-Scotland Ridge region of our Z-star PS-based eddy permitting GS9 configuration. For many of you that are not familiar with the multi-envelope method, this is a method that defines quasi-Eulerian computational levels that are adjusted to multiple arbitrarily defined surfaces that we call envelopes, rather than following geopotential of the actual topography. So with this method, we will have model levels that can be optimized to prioritize the prevailing physical processes, while significantly reduce horizontal pressure gradient errors and keeping a realistic topography. So in this case, on the sketch here on the left, let me show you a typical shelf break and continental slope discretized, in this case with 3 envelopes. I have not much time to go into the details, but we can chat later if you're interested. Okay, so as I was saying, we use this method to improve the representation of the Nordic seas overflows in the metaphysical permitting Chassignet configuration. In the red area there is where we localize multi-envelope levels. Otherwise, the model uses Z-star levels. In the green area, as explained before, the two vertical coordinate systems blend one to each other. And this is some results. So on the left-hand side is the OSNAP east array section of potential density. And the other two are the results from our models. The middle panel is from the control model using Z-star levels. And the other one is the one using localized multi-envelope levels. And we can see in the latter case, we are able to regenerate the dense water masses that are at the bottom of both the Immigrant Basin and the Atlantic Basin that are present in the observations, but not in the control. Okay, so our research question here are, can we use localized multi-envelope as coordinates within a Griff zooms to successfully implement vertical nesting in realistic applications? Then what is the impact of using vertical nesting along with horizontal nesting? And finally, what is the cost that we pay for it? So yes, let's go to the experiments. Our parent model is our GS9 configuration at 1/4 degree resolution forced by JRA 55 reanalysis. We implement a Mediterranean outflow Griff zoom at 1/20 degree resolution, 75 levels as the parent. So in this case, is a 5 times refinement in space and time. Similar physics to the parent, apart from few differences we can discuss later if you're interested. The main point is that we are comparing two configurations. One is using in the zoom Z-star levels with partial steps. The other one is using localized multi-envelope as coordinates, which are localized in the red area there. Doesn't work, okay. While in the white area, we use the Z-star levels with partial steps, and in the green area, the two coordinate systems blend one to each other. The simulations are long 40 years, more or less. Yes, here I'm just showing you how the grids look like. Left-hand side, the control, using in the zooms, Z-star levels with partial steps. Left-hand side, right-hand side is the one we localize multi-envelope levels. We are using, in this case, 5 envelopes. We can discuss the details later. I would like just to show you the results, which I think are more interesting. Yes, first we assessed the horizontal pressure gain errors. So we conducted 3-month-long simulation with no external force, no explicit diffusion, and initialized with a density profile only function of Z. The analytical solution for this kind of problem should be 0 meters per second for the ocean currents. However, because of the discretization error, when we use not geopotential coordinates, we will develop spurious currents. And so here I'm showing you the time evolution of spurious currents. In blue is the maximum value. In dashed yellow is the 99th percentile, and in dashed red is the average value. So we can see that the maximum currents after 90 days are less than 4 centimeters per second, but more importantly, the 99th percentile value shows that spurious currents in general are less than 1 centimeter per second. So this shows that those maximum values occur only in very few grid points of the zoom. So we were quite happy with that. Okay, so I will show first the solution inside the zooms, and then we will have a look at the impact of the zoom on the parent solution, because as I was saying, these are two-way zooms. So the solution of the zoom will update the solution and correct the solution of the parent at each time step of the parent in the location where the zoom is implemented. So we start with the bottom absolute salinity. Left-hand side, this is how the Mediterranean outflow should look like. So we will see that when the dense salinity plume cascade along the continental slope encounters rough topography. So there are many branches where the plume splits. And this is actually captured in the zoom using localized multi-envelope levels at the far right, while in the middle we can see that the model using Z-star levels is not able to capture and to represent all the little branches. Okay. Now, absolutely salinity transect. This is from the Simone 2002 campaign. The cross-section is shown there is between Portugal and Africa. So left-hand side is the observations, and then there are two panels are the models. In the middle, the one using in the zoom Z-star levels with partial steps. Right-hand side, localized multi-envelope levels. Both zooms represent a Mediterranean overflow that detaches from the bottom topography at the right depth, but the one using Z-star levels simulates a plute that is too saline with the solution, while the solution of the model using localized multi-envelope level agrees better with observations. Yes, finally for the zoom, we have a look at the eddy kinetic energy at 1000 meters. So we can see that in both zooms, the eddy left-hand side observations and then our models. In both zooms, the eddy kinetic energy at 1000 meters is too weak. You can see from our color bar, which is roughly a factor of 3 too weak in comparison to the shading of the observations. And we think that the reason is that in this case, in this area, the mesoscale activity is represented by MEDIs, which have a radius between 10 to 50 kilometers. So at 1/20th degree of resolution, which roughly corresponds to 4.5 kilometers, the smallest MEDIs can be barely resolved. However, we can see that the eddy kinetic energy of the model using localized multi-envelope levels agrees better with observations in comparison to the one using Z-star levels, both in terms of magnitude and location. Now, let's have a look to the parent model. So upright is the observations, up left. Upright is the model, is the control model not using a GRIF. So we can see that the control model without a GRIF simulates a Mediterranean overflow that is too weak and shallow. Then on the bottom, we have at the left the parent model exploiting the benefit of the 1/20th degree zoom with the using Z-star levels, while on the right-hand side is the parent model exploiting the benefit of the zoom with localized levels. And we can see that the solution of the zooms consistently feedbacks to the parent model, improving the Mediterranean overflow, especially in the case of the model where the zoom uses localized multi-envelope levels. Now, let's have a look at the surface circulation. So left-hand side, we have geostrophic currents reconstructed from SLA from Abiso observations. And then we have the solution, the surface currents from the model not using a GRIF, and then from the model using a GRIF with partial steps, and finally the model using a GRIF with localized multi-envelope levels. So we can see that both models using mesh refinement are able to simulate an absorbed current that agrees well with the Abiso geostrophic currents, while in the control model, the absorbed current is totally missing. And this is a signature of the well-known beta-proof mechanism that was theoretized first and then shown in many modeling studies previously. So we were quite happy that we could, improving the Mediterranean overflow, replicate both theory and observations. Then finally, I want to show you the impact of improving the Mediterranean overflow on the absolute salinity biases in the North Atlantic. So here our biases are assessed against the WA13 observations, as climatology. We start at 500 meters, so we can see that the parent model has quite large salinity biases on the east subtropical North Atlantic and in the Ladorot Sea. While when models using mesh refinement can significantly reduce the strong biases, at this depth, there are small differences between the two zooms. So the models using different zooms with different vertical coordinate system, and it seems that there is not a clear winner. However, if we go at 2000 meters, we can see that in comparison to the 1/4 degree model, the model exploiting the benefits of the zoom with ZPS has larger positive biases in the eastern subtropical North Atlantic, a smaller positive bias in the western subpolar North Atlantic, while the model using localized multi-envelope level in the zooms has reduced positive salinity biases in the entire subpolar North Atlantic, and is a little bit too salty in the central and western part of the subtropical North Atlantic. So I will finish with some computational considerations. So how much will this cost? Here I'm going to show you the simulated years per day of the control model using no AGRIF, while in green, in blue. In green is the model using the AGRIF zoom with Z-star levels, and in red is the model using the AGRIF zoom with localized multi-envelope levels. So we use the same number of CPUs for the three configurations, and we can see that we can have large improvements in the entire North Atlantic, especially when combining a GRIF with localized multi-envelope coordinates with small additional computational cost. And the vertical nesting seems to have little detrimental impact on the efficiency of the model. Okay, so in conclusions, yes, so we have used the localization method to successfully implement multi-envelope terrain-following coordinates in a 1/20th degree AGRIF zoom of the Mediterranean overflow nested in a 1/4 degree global configuration applying satellites with partial steps. Local multi-envelope coordinates are a viable option to implement vertical nestings in realistic configurations. Using localized multi-envelope terrain-following levels allow to reduce a Mediterranean overflow that agrees much better with observations. Two-way horizontal vertical nesting method seems to be a viable option to implement multi-scale capabilities in structural quasi-linear models. The computational cost for a single small zooms using the maximum space and time refinement factor is small. Now the question is, how efficient is running multiple nests in parallel? And yes, finally, we'll see that improving the representation of the Mediterranean overflow and associated mesoscale activity has large non-trivial impacts on the entire North Atlantic. The Mediterranean outflow seems to play an important role on the salinity biases documented in many eddy permitting rich ocean models. And I will just leave you with, or there is no video? There is no video, okay.
Okay, thank you, Diego. Questions?
Thanks, Diego. Nice talk. I wonder how much of the remaining bias, or what's the interaction in the biases between, if you're getting a better representation of the overflow, do the biases become more sensitive to your upstream properties, how you're actually doing in the med itself?
Okay. So we think, as you can see here, yes, especially here, so improving the Mediterranean overflow has an impact on this subpolar gyre, but we worsen a bit on the interior part of the subtropic. So we think that there is an indication that the mesoscale activity there should be also important. So what we are considering is, to have several nestings to address this issue. So I think here what is showing is that, yes, we are compensating errors in our configuration, that then if you improve something, we'll break this compensating error. So you show what are the problems on the regions.
So for this, I would have thought that doing a better job with the Denmark Strait overflow would have also strongly influenced what you're getting in the North Atlantic here.
Yeah, so in this study where here, where we tried this, so where we localized the multi-envelope there, we could actually improve the representation of the overflows, but we actually found that there was a strong salinity bias that was affecting the overflows. So we could improve the density, but if you look at the tracer, the salinity especially is too salty. So that's why I started to look around and to see where this salinity bias come from. And I think we are showing that they're not locally there. And this is more, so the subtropical gyre and the subpolar gyre are linked, and these biases are wandering around in the North Atlantic.
So, I mean, it's related to maybe Peter's question. So at most of these overflow, whatever the comparisons and whether you get good overflows or not will strongly depend upon the source water properties. If you don't have the fluxes right or source waters, it doesn't matter how good your
the coordinates cannot be miracles.
Right. They cannot correct for that error. The second comment that I was going to make was, do you have newer observations of the Mediterranean, because you are using almost 20-year-old stuff?
So to be honest, I finished the simulation 1 week before coming here.
Okay.
This is the first time I found, so I used that.
Okay.
Next question.
It's more an answer to your question. So back then, there was a huge effort to try to understand MEDIs. And I guess there was also plenty of funding, because literally people would see structures and just sail there and just drop drifters. So there are really good experiments and drifters that were tracked all across the Atlantic. And I don't think there have been any more observational studies since there.
Okay, thank you very much, Diego. Okay, so we are now about to have our penultimate discussion. This is the last session discussion, and then we have a general discussion after the break. But before we do so, can we all turn around, look at these two young gentlemen at the back there, and give them a big round of applause for handling our AB? I don't know if you've noticed, but we're using a parallel in time algorithm for doing the thank yous. It's really clever. Okay, so we're going to move back. We're moving into the discussion session. We're now going to discuss in general, the last 5 talks, I think it is. So we heard about adaptive coordinates from Andy, hybrid coordinate methods, numerics from Mats, a comparison of high common MOM6 with many improvements from Alan Wallcraft, a design of strategy for spacings from Gabriel, and then this multi-envelope hybrid topography from Diego. So we've just heard about all of that, and now let's have some general discussion. Any thoughts? We've got the questions up here on screen. There's only 5, right? Yeah. What are the big challenges? I think we've got it perfect now, haven't we?
Yeah, on the first one, we've heard multiple times the benefit of having a coordinate that allows following the isopycnals and minimize spurious mixing. And then there were a few talks, and there has been a few papers that talk about spurious mixing. But I don't have it clear, like we don't have a universal metric for quantifying spurious mixing. What is needed for us to get there? Can we come up with some kind of test to quantify spurious mixing?
I think just wait a little while. So Jan Zieker worked on a method to give you an unequivocal location of where spurious mixing was occurring, and he's showed me the theory, and I can't remember all the details, but I think he's pretty optimistic that he can put that diagnose offline or put that online in the coming 6 months or so. And that'll give us a really good metric that we can test across, different implementations and different coordinates. So
I think Steve's going to.
Well, the Burchard group came out with this variance approach, but it's relevant really for just dissipation in general, and it doesn't tell you the difference between dipycnal and isopycnal. So if you're running with a temperature-only model, like Andy was showing, then it's sufficient, but it's not good for general models where you have TNS, and so the work that Jan might be useful for that. I think it is.
With respect to the first question, I'm still a bit floored about all the stuff about vertical coordinates that I heard. And I'm wondering, the solution, what Stephen showed us, this is the end of is a brilliant piece of work. This is superb. But I'm wondering if this is a singular solution, because, who else than the 3 of you could build that? And I'm wondering how institutes like ours, if we move to generalized vertical coordinates or to isopycnal based, this is such a big effort. This is like, to me, it appears you want to renovate your kitchen and you build a new house. This is,
if I may comment,
it affects each and everything.
It's just pure applied math. You're going to get really excited about it now that you've seen it.
No, I'm relieved. Thanks.
I think, as you heard from both Alan and from Mats, the details are going to. But that's true of anything we do in numerical. The details always matter, and they're tricky. But it's no different to normal life.
It's a global change. It's not. If you have it isolated in some modules or algorithmic elements, fine. But this really that addresses everything, and that worries me. So have you thought about how to transfer that knowledge to others? Except all the 30 tricks you did, except that the stuff that is written in papers.
So this is Bob Hallberg. So Steve Griffies' tutorial paper lays out all of the details, as many as we could do. And because Steve is such a good writer, it's really well worth reading. The big challenge, though, is that your underlying dynamic core has to be able to handle vanishing layers that vanish in arbitrary times and arbitrary places. And that's one that is a particular challenge, because it gets in the way of the use of some numerical techniques that assume that you have, for instance, layers that exist everywhere so that you can interpolate in the horizontal, or that you have effectively the coastlines of your vertical, basically your horizontal slices that don't vary with time. If you have numerics that can handle essentially the wetting and drying of layers. The rest of it flows relatively straightforwardly.
The relatively in your sentence makes me nervous. I mean, what I clearly lack is, I mean, the amount of let's say, of intuition you have, how isopycnal physics, how that happens. I don't have that. And if you don't have that, if you have not grown up with that, then I imagine it's quite difficult to put all the pieces in place so that the whole thing gets these nice solutions. I mean, I would be worried, for example, at the transition between Z-star and isopycnal. What do you do there? There must be some strange things.
Let me also just caution you that the method that we're talking about here from Steve's paper, that's just one algorithm. That's the Lagrangian remap method. There are other approaches. NEMO uses coordinate transformations. You know, there are other strategies, and those are just a matter of changing equations and then discretizing them. So it's not all complex. It doesn't have to be.
Yeah, just relatively, I know.
Yeah, the relative is important.
Add a related comment maybe to that. I mean, one of the things that when we were going through, I mean, Gustavo can speak to this better than I can probably. When we were deciding whether to go with Z-star or hybrid coordinate system with MOM6 within the CESM3 context, we needed to be careful with our client base, right? The community, because Paleoclimate Group was worried that the choice of target densities or whatever would create a problem. Present day climate is something. And then if you go to future climates, then it's a different, again, density structure. And how do you handle these things robustly? And that's why Alistair has been visiting us to partially answer that challenge. So it comes with its challenges.
Thanks. Just on the point about paleoclimate and isopycnal layer models, or hybrid. I think what you can do, and not that I've done this, but you can sort of make a volumetric analysis of the ocean. And so if as the whole ocean is warming or cooling, you still want to have the same amount of volume within certain layers. And again, this is something that Jan Zika has thought a lot more about than.
The catch is that you can do that. And I think that's one of the approaches that Alistair and others are following. What do? Do you create PI control, pre-industrial control, historical control? Do you check their equilibrium climate sensitivity again in a coupled simulation? It brings another sort of group of simulations that you need to, because you can't just change the grid and tell paleoclimate people, go ahead and use it, right? You need to evaluate the code in certain like standard pre-industrial or present day or whatever historical simulations. So that creates additional complexity.
No, something else.
Are you following on that?
I have a microphone.
Oh, wow. Well, that was fast.
But I can take two. Following up from Peter's question, it looks all great, but I'm not able, at least from the talks here, to think about the consequences. And of course, being a person dealing with data assimilation, I start to wonder, what are the consequences for data assimilation? And dealing with agent models, I'm pretty sure that changing the layers, you do this, will cause huge problems with agent models.
Anybody who can answer that question? Or is Dan here? No.
Again, that Dimitri changed the subject, but I'll say for the ensemble common filter we're using at GFDL, what we've done is we've remapped the entire state, everything we need gets remapped to a fixed grid. So the model is doing its thing in its own coordinate. But the adjoint, I know, and so the adjoint would not handle that very well. Yeah. Dimitri.
A few comments on number one. I'll start with gains. So I really appreciated hybrid coordinates working on high latitudes. I participated in the Arctic Ocean Model Intercomparison project, and HiCom did an awesome job representing the water masses. Compared to other models, most of them are Z levels, they fail to represent the water structure, especially in the subpolar North Atlantic. The major challenge that I see with hybrid coordinates is not easy to use. They're not user-friendly, especially nesting into bigger domains. Data assimilation, I worked at EMC. Every day we try to improve the data simulation in HiCom. Yeah, the way data simulation is done is everything is mapped on the fixed layers, the simulation is done there, and then everything has to be remapped back onto the hybrid coordinates, and it's a big challenge.
So this is Bob Hallberg again. That was one of the big obstacles to the adoption of a hybrid vertical coordinated GFDL, is that it's hard to use. But if you look at people who are using and developing models, the number of people developing is relatively small. The number of people using them is large. And so one of the things that we did is we made all the diagnostics available, remapped right back to a Z coordinate for people to use if they want to. And that has been fairly effective. Moreover, if you're doing things like time averaging, the average of a fixed depth is well defined. The average of a layer that sometimes exists and sometimes doesn't is not. So part of it is trying to separate all of the complexity associated with the vertical coordinate from what end users who don't necessarily want to know anything about the internal details of the model have done. For the people developing, we can often isolate specific parts of the model, and so you don't necessarily need to know all the details.
Yeah, that's correct. I was talking more from the point of view who run the models. Working with hybrid coordinate models is much more difficult than with the Z-level models, for example.
Before I have Graham take up, Kate, you're taking notes? Thank you. Go ahead.
Yeah, just to follow on from Bob's point, because I can't miss this opportunity to bang on this drum, is that the budgets don't close on the remapped grids. So the heat, thickness, salt budgets, because of these issues that I tried to highlight yesterday, as Keith's work has shown. Not that that's necessarily a problem, but as a user, you know, you're trying to, as a user, is necessarily wanting to use something if they want to use closed budgets for temperature or so on. So,
if I may just redirect your attention, that kind of gets to maybe the fifth question. I mean, if the solution's better because of using a very complicated system, is it worth it if you can't analyze it?
I was going to ask you the same question, actually.
What's the question? So you have to
asked
answer.
it for me. I mean, if in terms, not just using it, as in whatever somebody not maybe necessarily familiar with the hybrid coordinate system, adding something simple like a horizontal diffusion is a nightmare.
Well, it's simple in a geopotential coordinate model, but isopycnal diffusion is complicated in that model. So, I mean, it's relative. I said it in my, another relative here. I said it in my talk that, what are you pointing at? Okay. Okay. That these models are relatively new in the sort of high-end climate context. And I think that smart people like Graham and Spencer and Andrew Shao and others that are focusing on the analysis questions are identifying issues and hopefully going to help fix those issues. You know, Keith Lindsay's ideas and so forth. I think it's a matter of time. I'm hopeful that these black boxes of a good model is going to be on, you know, it's going to be a little less opaque.
Elizabeth.
So it's Elizabeth from Wisconsin. A quick mention of an example that I'm familiar with right now that hasn't been brought up is how do you get students working with these kind of models? So I'm familiar with a grad student who wants to do an experiment. So take some ocean model and do something that requires a minor manipulation in, you know, depth structure. But she doesn't have that much time left in grad school. So it's really, you know, influencing which model she's using. And so from, you know, the CSM perspective, I hear a lot about, hey, let's move to the new CSM3 framework. Let's start using the MOM6 versions, but that's not necessarily a good use case for her. So I think I would encourage, you know, think about students with these kind of experiments that they might want to run with this kind of framework.
I'll speak to that a bit on experiences in Australia of trying to involve students in modelling and model analysis, and we put quite a bit of effort into essentially lowering the bar to entry and making sure that students could pick up a model we'd release a configuration and it would just run on our national HPC. And in many cases, people can just essentially downloading a configuration from GitHub. That configuration just points to publicly available precompiled binaries for our code. And there's lots of documentation around how to build experiments, whether that's changing surface forcing or changing other things. And then there's been a lot of machinery also around the analysis, because it turns out a lot of people just want to use other people's experiments and look at the outcomes. So a lot of machinery around sharing code and to analyze the output. And after a few years of that, we found that actually a lot of the time students were supporting each other and we could step back and just let it all happen. That's, still required some effort, but I feel like that sort of a structure can be really helpful, particularly for students in the uptake of modeling.
Yeah, I think that's awesome. And it looks like the kind of community you all have built down there really supports that. But in this case, I think the issue is not with getting the model running or configured or any of that. It's specifically issues with how, as a student, do you deal with the vertical remapping for the kind of experiments that might want to be set up. And I don't think there's a necessarily clear, easy approach for that that's going to be effective on the timeline that we're forced into.
Yeah, I think so. So the atmosphere model here at NCAR CAM is also an ADL model, as I understand. But I don't think the users are complicating or saying that that is an issue. So I think also MOM6 and what we also surprisingly showed is that you can set it up as a set star or a P star model if you need to avoid that complication of having a hybrid coordinate. So I just think it is just a more flexible framework.
Yeah, so in response, I think it was Liz that mentioned how can students work with these models with the complicated vertical remapping. I guess you could ask that question about, say, MIT GCM. How do you work with MIT GCM if you don't understand the time stepping scheme of MIT? Well, at some level, you trust that certain parts of the code are something you don't need to understand completely to use the code. I don't like to say that, but I don't think there's anybody, maybe Bob is the only one that understands everything about MOM6, and maybe there's one or two other people that understand everything about other models, NEMO in particular, Garvin and others. But the community evolves and you start to develop experience, and experience translates into trust. And then, you find problems and you fix them. And I think that's kind of how it's going to be. It's not going to be that much of a handicap, I hope.
So one of the things that we've done to try to make it easier is if you're setting up a new configuration, you don't need to know anything about the vertical coordinate. You can just take a Z-space data set. The model takes care of remapping it into the vertical coordinate for you. It writes it back out. So if you really don't want to know anything about the vertical coordinate, modulo the fact that Keith Lindsay's innovations have been, yes, I heard you, Graham. But apart from that, and we'll figure out how to sort that out. But apart from that, you really don't need to know too many of the details. However, one great gateway for students is as a layered model. We use layered QG or layered primitive equations. You can run this with 2 or 3 layers. And now this is simple for GFD problems, and it's exactly the same model with the moving vertical coordinate. And so if you have students who want to get familiar with how the model is actually working, that is a tremendous gateway.
I was going to add that one sort of challenging area might be, we keep saying that, well, at least I keep saying that model developers are a dying breed. And if you want to have graduate students get interested in parameterization development and their implementation in a model, I think that is the challenge. Because I know that many people are interested in analysis and all that stuff, and maybe that can be addressed with some of the things. But getting students interested in staying in the field in model development with hybrid, maybe with GPU complications and all that stuff, that is going to be maybe quite a bit of challenge.
Okay, so hands up, students. I've got 3 microphones. No. I mean, I think he's saying it's hard for students to get to grips with models. I mean, is it?
Well, I'm going to repeat what Andy said, I guess. I think I was well supported by the stuff that had been set up ahead of me by both students ahead of me and the community in Australia. And I found some stuff was kind of hard. Like the regional modeling, boundary condition stuff was quite difficult. But then because there was the existing framework other people had set up, I could get to the point of fiddling around with the boundary stuff much more quickly than otherwise possible. Then I was able to help out, leaving behind some other tools for other students to use. So I guess that's my comment on what Andy said.
Thank you.
Yeah, I'm not a student, but I just want to support what Ashley's saying in the sense that I think that the most difficult thing as a student is feeling like you're stagnant and you've got no support. And so I think it really isn't about the complexity of what you're trying to dig into, it's whether or not the community is supportive of the challenge that you're facing. So I think, like, for example, Gustavo and the folks here set up the online, the MOM6 on the CESM forum, right? Like a space where people can actually, having a good supportive network for addressing complicated problems. So it's not about the complexity of the problem, it's about the supportiveness of the community.
So if I can just wrap up this conversation, I mean, that's exactly the point. The community is the way to solve this problem, but the community needs to exist. So there's a critical mass of people involved in any one model that lets things get rolling and start self-sustaining it. So I think in Australia, we've seen that go around CSM and around MOM6 for our sake, and NEMO is a very big community, and I think I haven't heard anyone complaining about how hard it is to use NEMO, so clearly that's the one you should start with. So can we move on to change topics? So remember, a lot of the conversations one of the sessions was specifically about mixing, and we've looked at diagnosing mixing in some posters. Is this the solution? Is this necessary? Is this the right way to go for climate? Are the methods good enough? Are they robust enough? Basically, number 3.
Yeah, thinking of hybrid coordinates and the complexity of the model getting more complex. So thinking embedded icebergs, sub-shelf cavities, how is that going to play with hybrid as is, like isopycnal and Z-star?
Beautifully. It is similar to the problem of having topography. It's similar to the problems of having layers that are vanishing or not because the density is changing. And then when you're looking for the analysis, you would remap it back to whatever coordinate you want to use for remapping. We suspect that by the time it's done and it's working well, it's not going to really add any new complexity.
It's incredibly complicated now, though, until we figure it out. You have to admit, right?
It's only complicated because we don't understand what we don't understand.
It's always simple in hindsight.
We have 5 minutes left. 4 minutes. Well, that clock is fast relative to my time. So, any new topics? Oh, let's take a poll.
Are the benefits of hybrid general vertical coordinates worth the added complexity and what you get?
Hands up if you think it.
No.
I claim you have to qualify that a little bit more. It's like generalized vertical coordinates does not tell you it's hybrid. It does not tell you it's Lagrangian or not. I think the question is Lagrangian, quasi-Lagrangian, or quasi-Eulerian. Yeah. That's the distinction we need to poll on here.
Okay. So based on Steve's modification or rephrasing.
So what's the
I would say Earth system modeling in general, and also extension higher resolution versions of Earth system models with biogeochemistry and all the bells and whistles.
And the question is Lagrangian methods, isopycnal style, worth it?
Worth it. What's that?
Okay, so this is a poll, not an opinion expression. Hands up. Is it worth the complexity of Lagrangian methods for?
Yes or no?
Yes.
This is yes.
Yes.
Okay, so
Wow,
about
that's
half.
surprisingly few. Okay.
Yeah,
So
about half, 50-50 maybe.
So can I ask another question? So if we're going for the super high res, well, do qualify. Oh, is there people no's? Okay. Who's no?
Well, there were quite a few no, didn't vote. So.
And then, okay, so the rest will assume, oh, I don't know. Okay. Yeah. So let's have some opinions now after that vote.
So besides the issue of when you have to have a student deal with something in the vertical, I'll just echo what Gokhan said about paleoclimate simulations. Like if you have to come up with a new vertical grid for each type of climate, that's a real problem when your purpose is to try to, understand really different climates.
Ashley said this, but it might not have been heard online. Also, missing W can be a real loss for users of the output.
I think the adaptive grid, if it works as we expect it, will be flexible to the density range, so will be suitable for paleo.
So long as you add W.
So paleo, do paleo people need W?
So I think that you have demonstrated that you can reduce asymptotic mixing with this method. So I mean, it's definitely worth it to pursue it. We probably don't know if it's now already now if every model should switch or if that is the only way to go. Like it's worth to have several different models with several different characteristics, and this is definitely a way that is worth pursuing.
You can get W. You just need to close the budget properly on the offline, on the diagnosed grid. So I mean that seriously, like the ALE approach does not mean that you can't get a vertical velocity. You can definitely get a vertical velocity. So there's no issue there. You just need to do it carefully.
Yeah, I was going to say exactly the same thing. And at lunchtime, we started to have a discussion on how to actually include W in MAP6.
I was just going to say, it seems based on Steve's talk, the jury is sort of out a little bit on 3, and maybe it will become, maybe the perfect model will emerge. But Steve showed something that seemed to suggest both high resolution and better vertical coordinate might be needed. So,
Graham, you said that you can get W with offline diagnostics. I'm just wondering why not include this as an online?
He said he misspoke.
I didn't mean offline. I meant on a diagnostic, on a coordinate that is not the native coordinate of the model. So as an online diagnosed budgets, yeah.
That devolved into a chaos. So we're never doing a poll again. We do not want to hear from you. So thank you very much for your opinions. We've actually run out of time, and so it's now, if you want to carry on, you may, but it's the break time, and so you lose access to the cookies and coffee. So thank you very much to everyone for this last session, speakers, discussions, and note taker. Now, you're not allowed to run away. This was the penultimate discussion. We have a final discussion, conclusions, recommendations, discussion starting at 4 o'clock. And are there any other announcements? Do not go outside because you will be shot by a camera. So one other quick announcement. The hike is starting at 5 p.m. Oh, no. When do you have, you're setting my time.
Yeah, we plan 5 p.m. where the refreshments are being served.
And I believe Greg's going to be leading the hike. In order to be done by 5, to the OMDP people, we're going to have the confidential business part immediately after this session. So approximately 4:30, and we'll be done as fast as possible so you can join the hike. Okay. No, emeritus can show up. The lurkers can't. So people who are actually on the list on the web page. So that includes the emeritus. Yeah. You wanted to avoid it. Okay.
Okay, so this is the last session. We were going to originally sort of summarize everything and all that stuff, but there has been so much discussion, which is really great. And then we have quite a few notes that they have done a great job, all the note takers. So thank you very much for all of those. So we are going to try to, well, I think we'll start Turi.
Taker now.
I don't think that there's a note taker now. Shoot, we forgot we got all the sessions, but not this one. Oh, great, and thank you. So the idea is essentially to come up with sort of a short summary of the outcomes of the discussions. And as the organizing committee, so we'll try to do that based on the notes that are written. And it was also with full schedule for all 4 days, we didn't really have time also to go over the notes in detail. So we'll do that in a calm way later. But we have a few questions that we can essentially sort of classify them as general questions. And I'll just go ahead and read them, and then we can participate in more discussions. So, does the current state of the art in ocean modeling serve the needs of society at large? This is with the background that many of us, especially at centers, we are trying to address the stakeholder or decision maker needs at really the local scales. And this can include like predictions as well as projection simulations. What new applications or problems can be or need to be tackled? Are we essentially addressing the right questions? 3 is sort of what I just said, I guess. As the society and stakeholders ask for local scale, reliable information, can a single model and framework deliver all that? That is, can a single model be used for global, regional, coastal applications? Is it even reasonable and doable? I think that's the question that I put there, but I don't know. What progress is needed in the ocean modeling community itself to advance modeling? Is the community too siloed? Are the communities regularly talking to each other? And what are the challenges and advantages of using different computational languages and architectures, such as GPUs versus CPUs for the community and science? Because after all, I would like to think that what we are doing is in service to societal needs. Not necessarily, I mean, we are trying to advance science and numerics and all that stuff, but I hope we are doing it for the benefit of the greater community or greater good. And we partially discussed this thing actually. Is this sort of, CPU, GPU, hybrid versus Z, whatever the level coordinate, is it delaying, is it creating tension in the community? And in fact, when I voted no for the hybrid, I didn't know that people were watching me that much. During the break, they were asking me why I voted no, but I had reasons, obviously. Anyway, so if you still have energy, I think these are sort of, we can start the discussion.
Number 4, are we too siloed? I think that this group right here is a great example where we're trying not to be too siloed. I think there's half a dozen model, sort of developers represented here, if not more. And I would hope that those of us who have the ear of program managers and so forth in the US and in Europe can continue to allow these kind of meetings to happen every couple of years, because it really is important. I think there's a lot of smart people doing things that are in their own code, and to share those ideas and to critique them amongst ourselves in a good way is essential for progress.
Eric? Regarding number 5, GPU, CPUs, could we draw some parallels on what happened when we switched from vector computers to parallel computing? I mean, I do not recall how long it took for the community to shift, but
Was it as drastic? I don't know.
Well, probably, I mean, our GPU is going to be around for long enough that we should all switch.
Yeah. I mean, again, my view on the GPU CPU thing is that even though many people in the community may not like necessarily GPUs, I'm worried. I mean, the reality is that given the technology, given NVIDIA's latest stock news was they made $30 billion and 15 billion of it was profit. I suspect that whether we like it or not, GPU is going to be forced onto the whatever, every single community. And I think we need to be ready, whether we like it or not. That's my own thinking.
I just have a broad statement about that. I think if you take a step back, what we've been seeing is something we should really celebrate, which is that hardware is being developed that's more and more specialized for computation. And I don't know, it doesn't matter what you call it, GPU, whatever. I think, you know, we hope that that will continue into the future. And so I think that just means more broadly that we have to be prepared for software to support multiple architectures if we always want to be running as fast as we can, I think.
Yeah. Speaking of, I was going to say also being siloed or not, I don't know whether we try to advertise it as much as possible. There's actually an AMOC related meeting that's going to happen in about 2 weeks in Hadley Center. And that's about AMOC and AMOC modeling and model deficiencies, diagnostics, and all that stuff. So there's going to be, like, I can't remember how many people we end up having, 50. And I think a handful of us, like Eric, myself, Anna, and Diego, and a few others, and you're not coming, right? We'll be there. So that's, we are trying to essentially connect the communities as much as possible during these meetings. And lots of NEMO group people will be there, I believe, if I'm not mistaken.
On number 5, I guess tying two other things that I've heard in other discussions, trying to, I guess, enticing or getting ECRs interested in the model development, getting their hands dirty. And then another person in another discussion mentioned people maybe feeling like it's hard to get recognition for diving into those problems. And I wonder if a non-ECR could comment on that and whether there's changes that they've experienced in the field or things that do need to change, if it's a cultural thing or problem with the field, or yeah, just what are your thoughts?
Alistair, do you want to take a crack at that?
Just connecting the dots of two things I heard. It's not.
It's a really good question. I mean, the thing that came to mind when you were speaking was we've actually had a fairly regular, persistent conversation at the centers about the modelers getting recognition for all of the development work they put into building a model. Because there was a time when sometimes they would write that paper about the method, and then the model would be used, and they wouldn't get any credit. They wouldn't be included in the papers about the using the models. And so there's a lot more awareness that that recognition is necessary for the hardcore developers who otherwise are beavering away and spending all their time coding and not writing the papers. That was what came to mind, but it's not exactly what you're asking. For the individual, I think that, I think there's now an opportunity which really wasn't there because the community and the software, and the resources weren't there for individuals to actually make contributions, because I think everybody here now is open source. Open source has changed its meaning. It used to be that you just put a tar file on an FTP server, but now you can truly actually contribute, and you would get recognition because your name is on that bug you added. So I think but that actually reminds me of another issue, which is one thing experience teaches you is you should just never be scared of getting it perfect. And you should never be scared that you shouldn't get it, that you have to get it perfect. Everything we add to the models is wrong. That is always wrong. So that's something that we don't teach enough, that it's okay to submit something when you're not quite sure if it's right, or even if you're convinced it's right, because
well, it takes a lot of experience to just get over that hurdle of worrying it that I'm submitting something that's wrong.
I mean, the real challenge, I think, is, just to answer your question, is model development, putting parameterizations in or putting diagnostic codes in is not easy. It takes time. And at the end of, I don't know, you spend as a postdoc or a graduate student putting in something, developing diagnostics, you may get only 1 or 2 papers, if that many. However, if somebody else just analyzes the simulation that incorporates your changes, that person can write 4 or 5 papers. And when they apply for a job, usually people tend to look at the number of paper counts. We look at the quality and of course too, but that's also, I think we are doing it ourselves in a sense. When we look at multiple applicants, somebody has like at this point, 5 or 6 papers coming out as opposed to 1. And it may give the other person an advantage as opposed to actual model developer. And that's, I think it's an issue.
And while Andrew's getting his microphone, I'll just add one thing. There is also awareness that we need to not just focus on the papers. So there's a lot more than just the model codes that need to be contributed to. So all these analysis packages, Pangeo, anyone contributing to XGCM, the water mass transformation software, all of that is actually something you'll get recognized on your CV. And so it's worth, if you put effort into a Python tool, submit it, add it to a package, you will, it will pay off. That's something, I think that's something that's changed.
I'm going to potentially embarrass a few people in the room here, but as someone who's on the cusp of being not an ECR anymore, I think, during PhD, I was not particularly interested in the science aspect of it. And then when I went to GFDL, I started working on like various code things. And at one point, Bob took me to the side and was just like, hey, look, like, what do you want to do with your career? Like, do you want to be a professor? Because if you do, you should stop doing this. But if you don't, there is a place for you in the community. And I think that is one thing that was extraordinarily valuable to hear as a postdoc who wasn't interested in becoming a professor, was feeling a little lost kind of in the community and just being like, oh yeah, like any little thing you do, like is actually improving things. And I think that was extraordinarily valuable for someone like Bob, someone like Alistair, someone like Steve to be like, yeah, there is room and space for you in this community. And it may be unsung. Don't expect to be a professor, but do the work and it's going to be valued and recognized.
Just following on that, it's important to acknowledge that the word development often in some communities you think it's not thinking, it's just doing, but that's quite the contrary. We all know that to be a good developer, you are really doing creative, hard thinking to get the model to work and to translate the PDE into the code and stuff. So I think we all appreciate that here, but it's important to keep emphasizing that these are really hard problems, and that they're hard because they could take a lot of thought, as well as a lot of just actually doing the work and testing the code and things like that. And so I can't say that enough. The word development is not a non-thinking job. It's often the most important thought job.
Any other comments? I'll go back to the first set of questions if people want to see them again. Dimitri.
Comment on number 3. Yeah, the second question. Single model can be used for everything. I think in theory, it's possible to have a single model, but I don't think it's a good idea. We don't want to use one hammer for all nails. Plus, I think it's very beneficial for community to have different models for comparison, for analyzing, to learn from each other. If there is no competition, there is no evolution. So I don't think it's a good idea.
I'd like to follow up the same thing there. Recognition is great. Having your work be valued is great. But of course, the thing that matters is being able to get a job. And I think a lot of the people that are asking this question, can we do everything with one framework,
are asking it with the ulterior motive of hiring fewer of us. And I think the appropriate answer then from this community is probably maybe, but why? Why should we do everything with one model? What's the motive here?
So I'm actually going to take a slightly different position, which is for the climate problem. It is essential that we have a variety of independent models developed by groups of intelligent people. We will never be able to validate our projections with observations. If we're projecting something by the end of the century, we have to make decisions now about what that end of the century is going to look like. And so having diverse approaches, and where those diverse approaches come up with similar answers, maybe they're a little bit reliable. Where they come up with different answers, maybe it's giving us an idea of what things are there that we still need to study harder, or maybe are simply unanswerable given the physical nature of the problem. But I think on the ocean side in particular, it is essential that we maintain a number. I don't know what that number is, but it's certainly well above 1, maybe less than 20, of diverse, independent, well-funded efforts at fully coupled climate modeling so that we can assess the robustness of our projections. And on the ocean side, we're smaller than the atmospheric side. There are a number of coupled models that use very similar versions of NEMO, OM6, whatever. But even if you're using the same code, I think it's essential that you choose different choices for how you want to treat physical processes or parameterize them. So where we have talks, for instance, about mixed layers, I think we had 4 or 5 different ways that we're approaching the mixed layer. They all had some differences. I think it's essential that we maintain 4 or 5. We should not be looking for the single best approach, but we should look for diverse approaches that are all broadly consistent with our understanding and with the observations. Because in the world of climate projection, we are the ensemble. We are what defines the PDF. And for a lot of questions, it's in the ocean, not the atmosphere. And so I think we owe it to ourselves and society to maintain diversity. Yes, talk, but maintain diversity.
I just realized you can read number 3 in 2 ways. One is, can one model be applied to, let's say, global or coastal problems? And I think this is an important thing for model development, to go outside, to have more than one application focus, just to stretch the model's capabilities and see what happens. When it comes to the whole community using a single model, then, I mean, I fully agree with Bob. Genetic diversity is very important. And I mean, if you look at the House of Windsor, then you see the outcome if you have insufficient genetic diversity. We don't want to end there.
From House of Windsor.
I'm very sure there's nobody here.
Is it quick, Mohamed? Yeah. Okay.
Don't know how to answer that, but I want to reply to Bob. I like that comment, but there's 2 processes that work against it, right? One is just centralization, right? You said multiple independent models that are well funded, and if they're not well funded, you centralize, right? You reduce the number of variations, right? Because it's cheaper, and then the end member is one model, and then the other reason is that same is true for climate modeling. If you shorten your time scale, if you do prediction of longer scales, it's actually very beneficial of one system, right? And you see that this prediction problem comes in more and more in oceanography or in ocean modeling, and that's why there's that's why there's a call for lesser variety, because it's hard to maintain.
Okay, thank you. So we have 10 minutes left. I just want to remind the note takers that please send them to Elisa, right? So we should have probably 9 of them, including this session. So we want to just spend the last 10 minutes. I thought that this workshop was extremely useful. I learned a lot, and I want to thank everybody for coming. And I just wanted to ask also, either we can ask modeling groups or whatever individually, what was if we say one single message, takeaway message that you got from this workshop.
And we'll start with the centers if no one's volunteering. Who's a center?
Steve. Bob. Do you want to say something? Yeah, I mean, we can bring in the early career researchers. What were their gains?
This is my personal view. What I've learned from this is that things are changing and are changing quickly. And we need to keep up with it. And I think Bob's comment on the fact that we need to rethink what processes were left or 10, 20 years ago were thought as not that important may need to be brought into the show.
I guess my takeaway is pretty simple. I think this has been an amazing workshop, and my takeaway is just to communicate more with everyone. And I'm out in Victoria. I'm kind of on the fringes of the continent, and I think it's awesome to be more connected to everyone.
Dan?
I take away that the advances on AI and the computing side are real and here now, and that modeling centers ignore them at our peril, both for scientific advancement and also from the usability front. You know, if a grad student can run the model 200 times cheaper or emulate it, they should, right? And we should be, lockstep to make sure that we're part of that.
Yeah, again, speaking as an individual, not my center. One of my main takeaways was we still don't know what the best resolution is. We still don't know how much we need eddies and how much we need eddy parameterizations. And that question has been along for a long time, and it continues to persist. And those are my major takeaways.
Following up on that, to me, it sort of came as a surprise that mesoscale eddy parameterization is still so actual. I thought we would overcome that by simply increase the resolution. And we'll talk about the sub-mesoscale here, but it's still the mesoscale that counts.
Yeah, so I was taken, the depth of the difficulty in the creative work that's going on with the numerics is really impressive in this field. And I don't know enough about other fields, but I think that probably we are at a cutting edge of certain pieces of numerical methods, because it's a hard problem to do what we're doing. I think it's really impressive what I've seen.
I was struck by how much we can learn from each other when we're willing to be a little bit vulnerable and talk about what isn't going well as what is, and talk in detail about what makes things work. I think there were an awful lot of things, but I'm going to leave with a better understanding of half a dozen things that are worth trying. And a lot of it is that we were willing to share a lot of the details. Nobody was really selling anything. There weren't any funding managers to impress. And I think this sort of communication is absolutely invaluable for the community.
I just want to also thank everybody for coming from faraway places, from Australia, India, and other, like Brazil, I think too, right? So that has been really, and Scotland, from the driest place in Scotland, sorry. I think that's really, what makes this meeting sort of, well, I don't know. So this has been organized as joint, oh, sorry. Yeah, I was just going to pass it to you, actually. It was organized as a Commodore Clivar OMDP meeting, but this is the third of the Commodore ones.
Yes, so this is the third Commodore. And so we had discussions. I think we have no big announcement now, but we will try to organize another, at least Commodore meeting in 2 years, probably in Europe. And this is all I can say for the moment, but there are discussions, so we'll see. So I'm not sure we will have any fund. The problem actually is true that the first two Commodore meetings, we were paying, for example, for the lunch, for conference dinner, whatever, for the room. We didn't pay for any early career scientist travel expenses. And this is this aspect that we cannot really do as a single.
I can't say enough about the contributions from US Clivar, particularly for this meeting, and Clivar. jointly from WCRP to International CLIVAR, from US CLIVAR, we got quite a lot of funds to bring in early career scientists with the US CLIVAR funds from US, from the international CLIVAR funds from WCRP for the international folks. And those were all towards early career scientists. So I think securing funding is quite important early on to bring in early career scientists and make sure that they are participating because they are the future. So what a cliche word. They are the
I think it would be great if the next COMMODORE meeting is in Europe, so we can rotate between the continents. Of course, more European community can also join, and yeah, we can have representation from that community as well. So the last one was in Hamburg, also which was co-sponsored by TRR project, which is a national project in Germany from DFG. So we're actually happy as TRR because we just got funded for phase 3, which is going to run for 4 years, which is about 15 million euros, also on the topics of energy consistent parameterizations for climate and ocean models and atmospheric models. So we would actually be happy to co-sponsor the next COMMODORE meeting if it's in. Yeah, so it can be in Germany or also a cool location somewhere in Europe. We can talk about that later.
Andy?
Yeah, I'd just add, I think it's especially valuable for us to come over here because, you know, if Victoria is remote, then, you know, Canberra is seriously remote. And I think it is great that you got funds to fund international students and early career researchers. It'd be great to do more there. I noticed the absence of Japan, China, Taiwan.
Hong Kong is here.
Hong Kong is here, but mainland China is not. And there's a lot of researchers in those places. So if we can extend invitations to those areas, that would be great.
So for the first workshop in Paris in 2019 or 18, we sent really emails to all the modeling, not maybe all, but a lot of modeling groups in Asia, and I think also in South Africa, and they didn't really reply for the moment. But maybe we should try again, and yeah, and probably for those of you who meet with those people, just tell them actually if they are willing to come.
Do you want to have the last word, Bob? Okay. Well, thank you for coming.
Yeah, well, I think that we should thank everyone else. Okay, so thank you all for coming and making this a great workshop. All brilliant ideas, good discussions, and you've all had you had to spend time to get here. So thank you all very much, and we'll clap for you. Stop.